Scientists just released a groundbreaking discovery that changes everything we thought we knew about the interstellar object 3 Atlas. Just 2 weeks ago on October 24th, they detected something that has never happened before in the history of radio astronomy. 3 Atlas transmitted a radio signature as it passed through our solar system. The detection was confirmed. The chemistry is real. Hydroxyl radicals water breaking apart under starlight. But here is what is keeping researchers up at night. The signal originated from the same patch of sky as the infamous WOW signal from 1977, and that is not even mentioning the 8 other anomalies documented, plus the trajectory deviations unexplained, and a detection window so narrow we almost missed it entirely. Stay with me because by the end of this late-night exploration, you'll see why this discovery changes everything. If these developments continue to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you are tuning in from, what time it is there, and what you think about this new development. You are the reason we can keep chasing stories like this. So thank you for having our back. Part 1, A Faint Signal from Deep Space. October the 24th, 2025, 4:10 in the morning, Universal Time. Most of South Africa still slept under a canopy of stars, the kind of darkness that makes you feel like you are standing at the edge of everything. But in the Karoo desert, 64 massive radio dishes stood awake, their surfaces tilted toward a patch of sky so close to the sun that observing it bordered on impossible. The MeerKAT radio telescope array, one of the most sensitive radio instruments humanity has ever built, was doing what it does best, listening to the whispers of the cosmos. And on that particular morning, it heard something that should not have been there. 2 absorption lines appeared in the data stream. Faint, yes, barely distinguishable from the background hiss of the universe, but structured, deliberate-looking. The frequencies were precise: 1665 MHz and 1667 MHz. If you know anything about radio astronomy, those numbers should make your pulse quicken. They're the main lines of hydroxyl radicals, the O molecule, a chemical signature that appears when water breaks apart under the harsh glare of ultraviolet light. This wasn't static. This wasn't interference from a passing satellite or a glitch in the equipment. This was chemistry broadcasting itself across hundreds of millions of kilometers of empty space, and it was coming from something that didn't belong to our solar system at all. The object in question had been designated 3I Atlas Catalog Number C2020. 5N1. The I stood for interstellar, the third confirmed visitor from beyond the gravitational boundary of our sun. It had been discovered earlier that year, racing inward on a hyperbolic trajectory that screamed outsider. Astronomers had been tracking it for months, watching it grow brighter as it approached perihelion, the point of closest approach to the sun. They'd measured its speed, calculated its orbit, analyzed its tail formation, documented its brightness variations, but nobody, not one person on Earth, had detected a radio signal from an interstellar object before. Ever in the entire history of radio astronomy, going back to the 1930s when Carl Jansky first detected radio waves from the Milky Way, this had never happened. Let's be absolutely clear about what hydroxyl radicals mean. When water molecules get hit by ultraviolet radiation from a star, they don't just evaporate peacefully, they break, they fracture into component parts. Hydrogen atoms go flying off in one direction, and hydroxyl radicals, those O molecules, linger behind like ghosts. They absorb very specific wavelengths of radiation, creating dips in the spectrum at exactly 1665 and 1667 MHz. It is one of the most fundamental signatures of water chemistry in the universe, and it is the same chemistry that makes life possible on Earth. Every drop of water in your body, every molecule that makes up 70% of you can break down into these same radicals under the right conditions. So when astronomers see hydroxyl absorption lines in space, they're seeing the fingerprints of H2O, the universal solvent, the liquid that made biology possible. But here is where it gets strange. This wasn't a random detection from some comet in the outer solar system, or a distant star forming nebula. This was coming from 3 Atlas, an object that had spent millions, possibly billions of years drifting through the lightless void between stars, carrying who knows what kind of ice and organic compounds on its surface. And now, as it swung past our sun, it was releasing those volatiles, and the radio telescopes could finally see what it was made of. For the first time in human history, we were getting direct chemical information from interstellar material, not by sending a probe to catch dust particles, but by listening to the radio whispers of molecules breaking apart in real time. The scientists who first saw the data did what scientists always do. They doubted. They cross-referenced the signal against databases of radio frequency interference. They checked for satellites in the area. They compared the detection time against known sources of terrestrial noise. They even pulled up records from 2 previous observation attempts on September 20th and September 28th, both of which had come up empty. Nothing. No signal, no hydroxyl, just silence. So why did it appear on October 24th? What changed? The answer, as it turned out, had everything to do with geometry and timing. 2 factors that would make this detection not just rare but almost cosmically improbable. And then someone noticed something else. Something that sent a ripple of unease through the astronomy community. The kind of coincidence that makes even rational scientists pause and wonder if the universe has a sense of humor. The sky coordinates where 3 Atlas was located at the time of the detection, the exact patch of celestial real estate from which those hydroxyl absorption lines emerged, fell uncomfortably close to another famous location, a region of space that had produced 48 years earlier the most famous unexplained radio signal in the history of the search for extraterrestrial intelligence. You probably know it by its nickname, the WOW signal. August 15, 1977, the Big Ear radio telescope in Ohio picked up a narrow-band signal so strong, so precisely structured that the astronomer Jerry Ehman circled it on the printout and wrote, "Wow," in the margin. It lasted 72 seconds. It never repeated. It came from the constellation Sagittarius. And despite decades of follow-up observations, nobody has ever definitively explained what caused it. Was it alien? Was it a comet? Was it some mere bizarre astrophysical phenomenon we don't understand? The question remains open. But now, nearly half a century later, another interstellar mystery was unfolding in almost the exact same neighborhood of the sky, separated by just 9 degrees of arc, close enough to make you wonder if something about that region of space attracts strange signals the way a flame attracts moths. Let me be clear, this is not a message. Nobody is claiming that 3 Atlas is broadcasting a greeting or beaming us a cosmic encyclopedia. The signal is an absorption line, not transmission. It is chemistry, not communication, but the structure, the precision, the sheer improbability of detecting it at all, combined with the eerie echo of the WOW signal, has created a perfect storm of speculation. Online forums lit up. SETI researchers started drafting observation proposals. The popular press ran headlines about interstellar whispers and alien chemistry. And in the background, the scientists kept doing what they do best. Measuring, calculating, ruling out the impossible, and trying to explain the improbable. So, here is the question that hangs over this entire story. The question that will shape everything we discuss in the next 15,000 words. When the universe speaks, how do we tell if it is natural or intelligent? How do we distinguish between the random noise of chemistry and physics and the deliberate signal of something that wants to be heard? And maybe, just maybe, the question itself is flawed. Maybe nature and intelligence aren't opposites. Maybe the line between them is far blurrier than we've ever imagined. Because this time, the whisper didn't come from a star or a pulsar or a black hole. It came from something passing through, something that doesn't belong here. Something that carried across the unimaginable distances between stars a message written in the oldest language in the universe. Water breaking apart under starlight. Part 2. The observation geometry and timing that made it possible. You need to understand just how improbable this detection really was. 3 Atlas at the moment MeerKAT picked up those hydroxyl lines was located just 3.76 degrees from the sun. Let me put that in perspective. Hold your fist at arm's length and extend your thumb. That is about 2 degrees of sky. Now imagine trying to observe something less than twice that distance away from the brightest object in the daytime sky. The sun floods the entire electromagnetic spectrum with radiation, drowning out everything around it in a blaze of radio noise. Most radio telescopes won't even attempt to observe that close to the solar disk because the interference overwhelms the signal. It would be like trying to hear a whisper at a rock concert while standing next to the speakers. But geometry, as it turns out, is everything in astronomy. The fact that 3 Atlas was so close to the sun didn't just make the observation difficult, it actually helped. Here is why. When an object moves through space, its velocity causes a Doppler shift in any radiation it emits or absorbs. If it is moving toward you, wavelengths compress and shift toward the blue end of the spectrum. If it is moving away, they stretch and shift toward the red. 3 Atlas was screaming through the inner solar system, at an angle, not directly toward or away from Earth, which meant its hydroxyl absorption lines were Doppler shifted away from the sun's overwhelming radio output. The measured velocity was negative 5.66 kilometers per second, a recession velocity that nudged those 1,665 and 1,667 MHz lines just far enough from the solar background that MeerKAT's receivers could pick them out of the noise. The line widths were equally telling: 0.9 to 1.3 kilometers per second, narrow, precise, repeatable across multiple scans of the observation window. If this had been instrumental noise or radio interference, the lines would have been broader, messier, inconsistent, but they held steady, like a tuning fork ringing at a single clear frequency. The data integrity checks passed every test. The signal was real, and it was coming from exactly where 3 Atlas should have been based on its predicted ephemeris, the calculated path through space that astronomers used to know where to point their telescopes. Now, let's talk about why earlier attempts failed. On September 20th and September 28th, observatories around the world had tried to catch 3 Atlas in the radio spectrum. Nothing. Total silence. No hydroxyl, no emission lines, no absorption features. Why? The answer comes down to phase angle and solar heating. In late September, the comet was still too far from the sun, still too cold for significant sublimation of water ice. The surface temperature hovered below the threshold where volatiles really start to cook off. But by late October, everything changed. The object was days away from perihelion, scheduled for October 29th, and the sun's radiation was hammering its surface with increasing intensity. Ice that had remained frozen for eons was finally warming up, cracking, releasing gas into the thin coma surrounding the nucleus. And with that gas came hydroxyl radicals, billions upon billions of them, forming a cloud that absorbed radio light at exactly the frequencies MeerKAT was designed to detect. The timing window was almost cruelly narrow, too early, and the volatiles haven't released yet. Too late, and the object swings behind the sun from Earth's perspective, becoming completely unobservable. October 24th fell right in the sweet spot. A brief interval when the geometry aligned, the chemistry activated, and the sensitivity of the instrument matched the strength of the signal. If MeerKAT had observed even 48 hours later, the detection might have been impossible. The solar conjunction would have swallowed the object entirely, hiding it behind a wall of radio interference that no telescope on Earth could penetrate. Let's zoom out for a moment and consider what this means for the broader picture of interstellar object detection. 3 Atlas is only the third confirmed visitor from beyond our solar system. The first Oumuamua passed through in 2017 and left astronomers scratching their heads with its bizarre acceleration and lack of a visible coma. The second Borisov appeared in 2019 and behaved like a perfectly normal comet, complete with a dust tail and predictable outgassing. And now we have 3I Atlas, which seems to split the difference, mostly cometary, but with enough oddities to keep researchers awake at night. The fact that we're detecting radio signals from it at all represents a paradigm shift in how we study these objects. Before this, we relied on optical telescopes to track them, spectrographs to analyze reflected sunlight, maybe the occasional infrared measurement to gauge temperature. Radio detections, never? It wasn't even considered likely. MeerKAT's sensitivity in the L-band, the radio frequency range around 1.4 GHz, makes it uniquely suited for this kind of work. The array consists of 64 dishes spread across 8 kilometers of South African desert, each dish 13.5 meters in diameter, working in concert to create an effective aperture far larger than any single telescope could achieve. The correlator combines signals from all 64 dishes in real time, filtering out interference, enhancing coherent sources, and producing spectra with enough resolution to pick out individual molecular lines. It is a technological marvel, and it is sitting in one of the radio quietest regions on Earth, protected by law from the kind of radio frequency pollution that plagues observatories in more populated areas. But here is where the story gets even stranger. The orbital path of 3 Atlas isn't random. It is nearly aligned with the ecliptic plane, the flat disk where most planets orbit the Sun. Interstellar objects, by definition, come from outside our solar system, which means they could arrive from any direction. The galaxy is three-dimensional, after all. Objects from the galactic halo should approach from steep angles, swooping down from above or below the plane of the solar system. But 3I Atlas, it came in almost horizontally, as if it were following the same flat geometry that governs the planets. That is unusual, not impossible, but unusual enough to raise eyebrows. Some researchers have speculated that it might indicate a local origin, perhaps from a nearby star system whose orbital plane happens to align with ours. Others suggest it is just a statistical fluke, the kind of coincidence that happens when you start detecting more of these objects and the sample size grows. And then there is the question that nobody wants to ask out loud, but everyone is thinking: could the geometry itself, the near-sun angle, the specific phase of volatile release, be amplifying something that wouldn't normally be detectable? Could there be a mechanism we don't understand? Some interaction between the solar wind and the outgassing ice that creates a structured radio signature purely by accident? The laws of physics allow for all kinds of unexpected emergent behaviors. Chaos theory tells us that simple systems can produce complex patterns. Self-organization appears everywhere in nature, from snowflakes to galaxies. Maybe what we're seeing isn't a message, but it is not entirely random either. Maybe it is something in between. A natural phenomenon that looks designed because the underlying chemistry and physics have their own intrinsic order. The perihelion approach on October 29th loomed just 5 days after the detection. As the comet reached its closest point to the Sun, solar heating would have peaked, volatile release would have maximized, and the entire object would have been wrapped in a shroud of gas and dust. If hydroxyl production scaled with temperature, then the signal should have grown even stronger in those final days before perihelion. But did it? That is one of the questions that follow-up observations are trying to answer. Assuming the geometry allowed for any observations at all during that critical window, the Sun is both the enabler and the barrier, heating the ice to release the molecules while simultaneously drowning out the signal with its own radio noise. SARAO, the South African Radio Astronomy Observatory, logged the detection within hours. The data went through their standard verification pipeline: automated flagging for radio frequency interference, visual inspection by trained astronomers, cross-referencing with known sources, consistency checks across frequency channels. Everything passed. The hydroxyl lines appeared exactly where theory said they should, with the correct Doppler shift, the correct line width, the correct relative intensities. This wasn't a fluke. It wasn't a mistake. It was real, reproducible, and profoundly strange, not because it defied physics, but because it confirmed that interstellar objects, these cosmic wanderers born in the icy outskirts of alien star systems, carry the same chemistry that makes life possible here on Earth. And now, for the first time, we could listen to it. Part 3. What exactly was detected? Chemistry, not a beacon. Let's get something straight right from the start. This is not an alien transmission. I know the headlines made it sound like we'd picked up a postcard from another civilization, but that is not what happened. What MeerKAT detected was an absorption line, not an emission. The difference matters a lot. An emission line is light being produced by a source, radiation being actively generated and broadcast into space. Like a radio station transmitting a signal, an absorption line is the opposite. It is a dip in the spectrum, a shadow where something has removed light at a specific frequency. Think of it like looking at the sun through a prism. You see a rainbow of colors, but if you look closely, there are thin dark lines running through it. Places where elements in the sun's atmosphere have absorbed specific wavelengths. Those are absorption lines, and they tell you what the sun is made of without ever having to touch it. The hydroxyl radical O is one of the most important molecules in all of astrochemistry. It forms when water breaks apart under ultraviolet radiation, a process called photodissociation. Take a water molecule H2O, hit it with high-energy UV photons from a nearby star, and it fractures into hydrogen and hydroxyl. The hydrogen, being light and fast, escapes into space. The hydroxyl hangs around longer, absorbing radio light at its characteristic frequencies, 1665.402 MHz and 1667.358 MHz. These are called the main lines of interstellar O, and they've been used for decades to study star-forming regions, supernova remnants, and yes, comets. Lots and lots of comets. Every comet in our solar system produces hydroxyl when it gets close enough to the sun. It is one of the primary observables that astronomers use to measure water production rates. You can't directly see water vapor in the optical spectrum because it doesn't emit or absorb visible light efficiently. But hydroxyl lights up like a beacon in the radio and ultraviolet bands. So when you want to know how much water a comet is spewing into space, you measure the hydroxyl and work backward. It is a standard technique tried and tested over decades of comet science. What makes the 3 Atlas detection special isn't the chemistry itself, it is where the chemistry is happening. 3 Atlas at the time of the observation had a surface temperature estimated at around 230 Kelvin. That is cold by terrestrial standards, about -43 degrees. but it is warm enough for water ice to sublimate directly from solid to gas without melting first. At that temperature, the ice begins to crack and release vapor into the surrounding space, forming what astronomers call a coma, a thin atmosphere of gas and dust that envelops the nucleus. The coma expands as the comet approaches the Sun, growing from a few hundred kilometers across to tens of thousands of kilometers, depending on how much volatile material the comet contains. And within that coma, chemistry happens. Water molecules break apart, hydroxyl radicals form, and if you are lucky enough to be listening with a radio telescope at exactly the right frequency, you can detect them. The signal MeerKAT picked up was not modulated. There was no pulse train, no repeating pattern, no variation in intensity that would suggest deliberate encoding. It was just a steady absorption feature, a dip in the background radio spectrum that appeared exactly where hydroxyl should appear given the comet's velocity and position. If this were a true techno-signature, something deliberately created by an intelligent civilization, you'd expect to see structure within the signal, information encoded in frequency modulation, amplitude modulation, phase shifts, something that screamed design. The 1977 WOW signal, for all its mystery, was narrowband and intense characteristics that made it stand out as potentially artificial, even though it never repeated. The 3 Atlas signal perfectly consistent with natural chemistry. Boring in a way except for the fact that it is coming from an interstellar object which makes it anything but boring. Let's talk about what a real artificial signal would look like just for comparison. In SETI research, the gold standard is a narrow band transmission, something far more spectrally pure than anything nature produces. Pulsars emit radio signals, but their broadband spread across a wide range of frequencies. Hydrogen clouds in space emit at 21 centimeters, but that line is broad too, shaped by thermal motion and turbulence. A deliberate transmission would be needle-sharp, occupying a tiny sliver of the spectrum because that is the most efficient way to pack information into a limited bandwidth. You'd also expect some kind of encoding, prime numbers, mathematical constants, image data, anything that distinguishes it from random noise. The hydroxyl lines from 3 Atlas don't have any of that. They're exactly as wide as thermal and turbulent motion in the coma would make them. Exactly as intense as you'd predict from the amount of sunlight hitting the nucleus. Exactly as Doppler shifted as the velocity measurements indicate they should be. But here is the thing. Even though this isn't a techno-signature, it is still profound. This is a biochemical signature from an interstellar object. Think about that for a second. For the first time in human history, we've directly measured the chemical composition of material that originated in another star system. We've confirmed that ice formed around an alien sun, carried across light years of empty space, still contains water, still behaves the same way our solar system's ices behave. The laws of chemistry are universal. The same molecules that make life possible here exist out there, drifting through the galaxy on comets and asteroids, and who knows what else. That validates one of the central assumptions of astrobiology that the building blocks of life aren't special to Earth. They're everywhere. Parallels with cometary observations are exact. When the European Space Agency's Rosetta mission studied comet 67P Swadhyumorpha-Gerasimenko up close, it detected water vapor, hydroxyl radicals, carbon dioxide, methane, ammonia, all the volatiles you'd expect from a dirty snowball heated by the sun. The Swift UV telescope, which observed 3 Atlas in the weeks leading up to perihelion, confirmed water sublimation signatures in the ultraviolet spectrum. Independent measurements from ground-based optical telescopes tracked the brightness variations and dust production. Everything lined up. This object was behaving like a comet, producing the chemical signatures that comets produce, releasing gas at the rate you'd expect based on its size and distance from the sun. The only difference, it didn't form here. It formed somewhere else, orbiting a star we'll probably never identify, and now it is passing through our neighborhood on a one-time trajectory that will fling it back into interstellar space at over 40 kilometers per second. The surface temperature of 230 Kelvin is perfect for sublimation. Too cold and the ice stays locked up, bound by molecular forces that require more energy to break. Too hot and you get explosive, outgassing sudden jets, potentially catastrophic fragmentation. 230 is the sweet spot, the temperature where water ice gently transitions from solid to gas, releasing volatiles in a steady, controllable stream. It is the same temperature range where comets in our solar system really start to wake up, growing tails, brightening, becoming the naked eye spectacles that ancient civilizations once interpreted as omens. 3 Atlas probably won't become a naked eye comet. It is too small, too faint, approaching the sun at an angle that keeps it mostly hidden in the solar glare. But for radio astronomers, it is a spectacular sight. A real-time chemical analysis of interstellar ice broadcasting its composition across the electromagnetic spectrum. No modulation means no deliberate message, but it also means something else. This is raw, unprocessed chemistry. If you wanted to hide a signal in natural phenomena, you'd need to modulate something, change something, encode information in a way that stood out against the background. The fact that the hydroxyl lines from 3 Atlas are indistinguishable from natural cometary emission suggests that either it is completely natural, which is the simplest explanation, or any hypothetical intelligence capable of manipulating chemistry at this level is so advanced that it can perfectly mimic natural processes. And if that is the case, if an alien civilization has the technology to create synthetic comets that behave exactly like real ones, then we're not dealing with intelligence as we understand it. We're dealing with something that operates on a scale so far beyond us that detection would be meaningless anyway. So here is where we land. The signal is chemistry. Hydroxyl absorption. Textbook stuff. Exactly what you'd expect from a comet with water ice approaching the sun. But it is chemistry happening on an interstellar object which elevates it from routine to historic. It proves that comets beyond our solar system can carry life's precursors across the galaxy. It demonstrates that water, the most important molecule for biology, exists in abundance throughout space, frozen into grains and pebbles and boulders that wander between stars, and it shows that with the right instruments, the right timing, and a little bit of luck, we can listen to the chemical symphony of the cosmos in real time. Because even if 3I Atlas isn't spitting out a message, it is broadcasting something equally important. Proof that the chemistry of life is universal, ancient, and written into the fabric of the galaxy itself. Part 4, Anomalies, Oddities, and the WOW signal echo. But if 3 Atlas were just a well-behaved comet following predictable physics, we wouldn't be having this conversation. The hydroxyl detection is only part of the story. As the object approached perihelion, researchers documented not 1, not 2, but 8 distinct anomalies in its behavior. Deviations from what you'd expect from a simple icy body coasting through the inner solar system. Unusual tail dynamics. Erratic brightness variations that didn't match standard models of dust production. Off-axis jets firing in directions that seemed inconsistent with simple solar heating. And perhaps most strangely, the formation of both a tail and an antitail. 2 opposing dust streams that suggested something more complex than ordinary outgassing. Let's start with the tails because they're the most visually striking. When a comet approaches the sun, solar radiation pressure and the solar wind push dust and gas away from the nucleus, creating a tail that always points away from the sun. Always. It is one of the most reliable features of cometary behavior. But 3 Atlas developed what observers described as an anti-tail, a secondary dust stream pointing in the opposite direction toward the sun. Now, anti-tails aren't unheard of. They can appear as perspective effects when Earth passes through the orbital plane of a comet, creating the illusion of a tail pointing sunward when really you are seeing dust grains that were released earlier and are now lagging behind the nucleus. But the symmetry in this case was odd. The main tail and the anti-tail had similar brightness, similar length, as if the comet was spewing material in 2 opposite directions simultaneously. That would require asymmetric outgassing jets firing preferentially from specific locations on the rotating nucleus, which in turn would require an irregular surface with concentrated pockets of volatiles. NASA's space weather reports flagged the tail dynamics as noteworthy. The main tail showed oscillations wobbling back and forth over the course of hours, as if the direction of gas release was changing with rotation, if the nucleus was spinning rapidly, and if active regions on the surface were facing different directions as it rotated. Then you'd expect the tail to shimmy and shift. But the magnitude of the oscillation seemed excessive. Rotational models suggested the nucleus should be spinning once every 8 to 12 hours, a typical rate for small cometary bodies, but the tail behavior implied something faster or something with a highly elongated shape that created torque as it rotated. Either way, it didn't fit the profile of a simple round snowball melting in the sun. Brightness variations added to the puzzle. Optical telescopes tracking 3 Atlas reported that its magnitude fluctuated by nearly 0.5 magnitudes over the course of a week, far more than you'd expect from rotational modulation alone. A 0.5 magnitude change corresponds to a 60% increase in brightness, which would require either a sudden increase in dust production or a change in the viewing geometry that exposed a more reflective surface. But the orbit was well known, the viewing geometry predictable. and no sudden outbursts were observed in real time. The brightness just changed smoothly but significantly, as if the comet were dimming and brightening in response to factors that weren't immediately obvious from the data. Off-axis jets are another clue that something unusual is happening. Jets are common on active comets. They're localized regions where sublimation is particularly intense, often concentrated near the subsolar point, the spot on the surface directly facing the sun. But 3 Atlas exhibited jets firing from locations that weren't directly illuminated, suggesting that subsurface heating was driving the outgassing. Sunlight would penetrate the outer layers of ice, get absorbed below the surface, heat the interior, and cause pressure to build until gas erupted through cracks and vents. That process can create jets pointing in almost any direction depending on where the vents are located. But it also implies a complex internal structure, layers of ice with different compositions and thermal properties, not a homogeneous lump of frozen water. And then there is the coincidence that refuses to go away. The sky position. 3 Atlas at the time of the hydroxyl detection was located at approximately 19 hours right ascension, -27 degrees declination. The WOW signal detected 48 years earlier originated near 19 hours 25 minutes right ascension 26 degrees 45 minutes declination. That is a separation of about 9 degrees, close enough to fall within the same general region of the sky in the constellation Sagittarius, near the galactic center. 9 degrees is not trivial. It is 18 times the width of the full moon, but on the celestial sphere, which spans 360 degrees in all directions, it is uncomfortably close. Close enough that when the news broke, SETI researchers started pulling up archival data, comparing notes, wondering if there was any connection at all. The WOW signal remains one of the most famous unsolved mysteries in astronomy. On August 15, 1977, the Big Ear Radio Telescope in Ohio recorded a 72-second burst of narrowband radio energy at 1420.456 MHz right next to the hydrogen line at 1420.406 MHz. The signal was so strong that it registered as a 6 on a scale where 1 is typical background noise. Jerry Eman, the astronomer reviewing the printout, was so startled that he circled the alphanumeric sequence on the computer paper and scrolled WOW next to it. Follow-up observations found nothing. Hundreds of hours of listening time over subsequent decades turned up no repeats, no similar signals, no explanation. Theories range from alien transmissions to interstellar clouds amplifying natural emissions to comets releasing hydrogen, though none of the explanations fully satisfied the data. Now, here we are nearly 50 years later with another anomalous signal from nearly the same region of space. Could it be coincidence? Absolutely. The sky is big, but certain regions get more attention than others. Sagittarius being toward the galactic center is a popular target for surveys, which means more data, more chances to catch something unusual. But the timing and the chemistry have drawn attention anyway. The fact that both signals involve radio frequencies, both involve unexpected detections, both come from sources that defy easy explanation, creates a pattern that is hard to ignore, even if it is probably meaningless. Avi Loeb, the Harvard astronomer known for his provocative takes on interstellar objects, described the hydroxyl detection as the first radio signal from 3I Atlas, carefully framing it as an interstellar chemistry milestone rather than a techno-signature. But the phrasing itself is loaded. First radio signal from an interstellar object sounds mundane until you remember that we've only confirmed 3 such objects, and 2 of them remained radio silent through their entire solar system passage. So why did this one speak? What makes 3 Atlas different? Is it richer in volatiles? Is it larger? Do we just get lucky with the timing and geometry? Or is there something about its composition, its structure, its origin that sets it apart? Skeptics predictably argue that this is just cometary behavior amplified by solar heating. And they're probably right. The simplest explanation, the one that requires no new physics and no wild speculation, is that 3I Atlas is a comet like any other, just one that happened to form in a different star system. The anomalies in its tail and brightness and jet activity are unusual, but not unprecedented. Comets are messy objects full of inhomogeneities and internal structure that make them behave unpredictably. The fact that we're seeing strange behavior doesn't mean the behavior is inexplicable. It just means we don't have enough data yet to build a complete model. But then MeerKAT's data shows something else. Stable line structure across multiple scans. The hydroxyl absorption appeared consistent in every observation within the detection window, ruling out instrumental error or transient interference. If this were a glitch, it would appear in one scan and vanish in the next. If this were terrestrial interference, it would show up at random times uncorrelated with the comet's position, but the signal tracked with 3i Atlas moving across the sky at exactly the rate the ephemeris predicted. Doppler shifted by exactly the amount the velocity measurements required. That level of consistency argued strongly for a real astrophysical source, not an artifact, and online as always the public imagination ran wild. SETI subreddits exploded with speculation. Was this first contact? Was 3 Atlas a probe? Could it be transmitting on other frequencies? We haven't checked yet. Mainstream media, to their credit, mostly got the story right. Interstellar object produces first radio detection. Hydroxyl lines confirm water breakdown on alien comet. That sort of thing. But the headlines blurred together, and by the time the story filtered through social media, it had mutated into scientists detect alien transmission from interstellar visitor, which is technically accurate if you interpret transmission as emitted radiation and alien as not from our solar system, but wildly misleading if you think it means deliberate communication from extraterrestrial intelligence. So, here is where we are, 8 anomalies, one of which is a radio detection unprecedented in the history of interstellar object studies, a sky position that echoes one of SETI's greatest unsolved mysteries, chemistry that is perfectly natural but also perfectly aligned with the building blocks of life, and a growing sense that even if this isn't aliens, even if it is just a comet doing comet things, the implications are almost as profound, because if it is not aliens, then what we're seeing is proof that the ingredients for life travel between stars on cosmic lifeboats, and that one day, billions of years ago, an object much like 3i Atlas might have delivered the water and organics that made Earth habitable in the first place. Part 5. Implications. If it were more than chemistry, let's indulge in a thought experiment just for a moment. What if the hydroxyl absorption lines from 3i Atlas weren't purely natural? What if buried in that chemistry there was something deliberate, something engineered? I am not saying this is the case. The evidence overwhelmingly supports a natural explanation, but science advances by asking what if, by exploring the boundaries of possibility. So, let's push that boundary and see where it takes us. If the absorption lines were deliberately engineered, we'd be looking at a form of communication that operates on principles completely alien to our own technology. Human radio transmissions are all about emission. We generate electromagnetic waves and broadcast them into space, hoping someone with a receiver tuned to the right frequency might pick them up. But absorption is passive. It requires a background source of radiation and a medium that selectively removes specific frequencies. To engineer an absorption signal, you'd need to control the chemistry of a comet or asteroid with extraordinary precision, manipulating the abundance and distribution of hydroxyl radicals to create spectral features that encode information. That is orders of magnitude harder than just building a radio. But let's imagine it is possible. Let's imagine a civilization so advanced that it can seed interstellar objects with specific chemical compounds programmed to release at precise rates when heated by a star. The information wouldn't be in the existence of the molecules themselves, which are common throughout the universe, but in their timing, their distribution, their ratios. Maybe the signal isn't in one set of hydroxyl lines, but in dozens of observations over time, a sequence that only reveals its structure when you watch the entire perihelion passage. Maybe the message is written in the correlation between different molecular species, hydroxyl and carbon monoxide and cyanide, all releasing in patterns that spell out mathematical constants or stellar coordinates. This kind of technosignature would be almost impossible to distinguish from natural processes without extensive observation. You'd need multi-wavelength coverage tracking every chemical emission and absorption line from the ultraviolet through the radio spectrum, building a complete chemical inventory over weeks or months. You'd need spectral resolution fine enough to catch subtle variations in line width or intensity that might indicate modulation. And even then, you'd be fighting against Occam's razor, the principle that the simplest explanation is usually correct. A natural comet with unusual but physically plausible outgassing patterns will always be a simpler explanation than an artificial probe disguised as a comet. Compare this with past technosignature hypothesis. Dyson spheres, those hypothetical megastructures that would capture all of a star's energy output, should produce distinctive infrared signatures as they radiate waste heat. We've searched for them. We found nothing that can't be explained by dust or natural stellar phenomena. Narrowband radio pulses like the WOW signal offer tantalizing hints but never repeat. leaving us unable to confirm whether they're artificial or just rare astrophysical events. Light modulation. The idea that an alien civilization might signal by causing deliberate dimming patterns in their star got briefly exciting with Tabby's star. But further observations revealed mundane explanations involving dust clouds and orbiting debris. What makes the idea of molecular absorption as communication so intriguing is that it exploits natural processes as camouflage. If you wanted to send a probe through a star system without drawing attention, disguising it as a comet would be brilliant. Comets are everywhere. They're ignored unless they get bright enough to interest amateur astronomers or threaten to hit something important. A probe cloaked in ice and dust, releasing gases exactly like a real comet could study a solar system up close, while everyone assumes it is just another chunk of frozen debris. The only giveaway might be subtle anomalies. The kind of details that only reveal themselves when you look closely. Unexpected trajectory adjustments, too precise chemical ratios, patterns in the outgassing that statistical analysis flags as non-random. But here is the energy problem. Manipulating chemistry at the molecular level requires enormous precision. Natural processes are messy, driven by thermodynamics and chaos. To create ordered patterns in volatile release, you'd need active control mechanisms embedded throughout the object. Perhaps nanoscale machines that regulate sublimation rates, perhaps exotic materials with engineered thermal properties that channel heat to specific regions on command. The technology required would be so far beyond our current capabilities that calling it advanced would be an understatement. We're talking about engineering at the atomic level across an entire object hundreds of meters or kilometers, across with systems robust enough to survive millions of years of interstellar radiation and temperature extremes. If that is what we're looking at, then the civilization responsible operates on scales we can barely imagine. And yet, when you ground back in the data, everything matches known cometary spectra perfectly. The hydroxyl line ratio, the relationship between the 1665 and 1667 MHz features, falls exactly where theory predicts for thermal excitation in a low-density gas. The line widths correspond precisely to the velocity dispersion you'd expect from molecules evaporating off a small body. The Doppler shift matches the measured heliocentric velocity within the uncertainties. There is no anomalous modulation, no hidden substructure in the spectral features, no frequency components that don't belong. If this is artificial, it is perfect, too perfect maybe, which pushes us back toward the natural explanation. Public reaction has been a fascinating mix of excitement and frustration. The excitement comes from the possibility, however remote, that we're witnessing something unprecedented. The frustration comes from the fact that it is probably just a comet doesn't satisfy the part of us that wants the universe to be stranger, more mysterious, more populated than it appears. Social media lit up with variations of "it is not aliens again." And why is it never aliens, which captures the cultural moment perfectly? We're a species hungry for contact, primed by decades of science fiction, to expect that first signal. And every time something unusual appears in the sky, we hope this will be the one. And every time the answer comes back, natural processes, physics as usual, nothing to see here. But maybe that response misses something important. Maybe we should redefine what counts as communication. Look at the natural world on Earth. Trees communicate through fungal networks, sharing nutrients and warning signals. Whales sing across ocean basins, their songs carrying information about location and identity. Bees dance to describe the location of flowers. None of these systems evolved to communicate with humans, but they're undeniably transmitting information using chemistry and physics and behavior to encode meaning. What if the universe operates the same way? What if there are natural processes that carry information across interstellar distances, patterns in the distribution of molecules, or the timing of stellar flares that encode something meaningful, not to us specifically, but to whatever systems are capable of reading them? From that perspective, 3 Atlas is communicating. It is broadcasting its chemical composition, its thermal history, its origin story written in isotopic ratios and volatile abundances. The message says, "I formed in the outer reaches of another star system. I was ejected by gravitational interactions, perhaps a close encounter with a giant planet or a stellar companion. I drifted through the galaxy for millions of years, cold and dark, accumulating cosmic ray exposure and interstellar dust. And now I am here, briefly illuminated by your sun, releasing the ices I've carried across light years." That is not intelligent communication in the sense we usually mean, but it is information nonetheless, preserved and transmitted across vast distances and timescales. The philosophical question becomes, if nature is already full of signals, and we're just starting to learn how to read them. Does the distinction between natural and artificial even matter? Or is it a false binary imposed by our limited perspective? Maybe intelligence isn't a separate category, but an emergent property of sufficiently complex chemistry. Maybe the line between life and non-life, between signal and noise, between message and chemistry is far blurrier than we want to admit. Maybe we've been searching for communication that looks like our own, electromagnetic waves carrying encoded data, when the universe has been communicating all along in a language we're only beginning to recognize. The language of molecules assembling and breaking apart, of gravity sculpting orbits, of light carrying information across billions of years. So here is where this thought experiment leaves us. The hydroxyl lines from 3 Atlas are almost certainly natural chemistry, nothing more. But nothing more undersells what that actually means. This is direct chemical analysis of interstellar material. The first time we've been able to sniff the composition of ice from another star system using radio spectroscopy. It confirms that water, the molecule that made life possible on Earth, exists in abundance beyond our solar system's edge. It proves that comets can preserve volatiles across the hostile environment of interstellar space. And it hints that maybe, just maybe, life's ingredients aren't rare cosmic accidents, but common cargo on wandering icebergs that crisscross the galaxy delivering organic chemistry wherever gravity pulls them. If that is not a form of communication, if that is not the universe telling us something profound about our own origins, then I don't know what would be. Because what is coming next may prove that the universe isn't just talking, it is teaching us where we came from. Part 6, Interstellar Visitors and Why 3 Atlas is Special. Let's zoom out and put 3 Atlas in context, because understanding why this object matters requires knowing just how rare these visitors actually are. As of late 2025, humanity has confirmed exactly 3 interstellar objects passing through our solar system. 3. Out of the billions of asteroids and comets we've catalogued over centuries of observation, only 3 have proven beyond doubt that they came from somewhere else. That number should terrify you, not because interstellar objects are rare, but because it suggests we're mostly blind to them. Simulations predict that at any given moment, dozens of interstellar visitors should be passing through the inner solar system, but they're faint, fast, and easily mistaken for ordinary solar system debris until someone calculates their orbits and realizes the trajectory is hyperbolic, unbound, approaching from velocities that indicate extrasolar origin. The first confirmed visitor arrived in October 2017, designated Oumuamua, a Hawaiian word meaning scout or messenger. It was spotted by the Pan-STARRS telescope in Hawaii as a faint point of light moving rapidly across the sky. Initial observations suggested a rocky asteroid maybe 100 meters long, tumbling end over end. But then things got weird. As it rounded the sun and headed back toward interstellar space, it accelerated, picking up speed beyond what gravity alone could explain. Not a lot, just a tiny nudge, but enough to be statistically significant. Outgassing from cometary ices could explain it, except Oumuamua. Mua showed no coma, no tail, no spectroscopic evidence of volatiles. Whatever was pushing it remained invisible. Theories proliferated. Maybe it was a hydrogen iceberg that sublimated without leaving visible traces. Maybe it was a solar sail, a thin reflective sheet pushed by solar radiation pressure. Maybe it was shaped like a pancake or a cigar, geometries that would experience unusual radiation forces. We'll never know. It is long gone, receding into the darkness at 26 kilometers per second. And we didn't spot it early enough to get the observations we needed. Twy Borisov appeared in August 2019. Discovered by amateur astronomer Gennady Borisov using a homemade telescope in Crimea. Unlike Oumuamua, Borisov behaved exactly like a comet. It had a coma, it had a tail. Spectroscopy revealed water vapor, carbon monoxide, cyanide, all the volatiles you'd expect from a dirty snowball heated by the sun. Its orbit was unambiguously hyperbolic, coming in from interstellar space at 32 kilometers per second, which meant it wasn't just passing through. It was screaming through, barely slowing down as it swung around the sun. Observation showed it had a nucleus about half a kilometer across, composed of ices similar to comets formed in our own solar system, suggesting that comet formation processes might be universal. It was in a way disappointingly normal, exactly the kind of object you'd expect if you ejected a comet from the outer reaches of any planetary system. No anomalies, no mysteries, just confirmation that cometary chemistry works the same way everywhere. And now we have 3 Atlas designated 2020, 5N1 discovered by the Atlas survey in July 2025. Its hyperbolic orbit was confirmed within weeks, revealing an inbound velocity of 42 kilometers per second relative to the Sun, fast enough that no gravitational interaction within our solar system could have accelerated it to that speed. It came from outside, period. But unlike Borisov's straightforward cometary behavior and Fabio Oumuamua's bizarre acceleration, Atlas occupies a strange middle ground. It shows cometary activity. Yes, a coma outgassing the hydroxyl lines we've been discussing, but it also displays anomalies in its brightness, its tail dynamics, its rotational state, features that don't fit neatly into standard models, and now it has produced the first radio detection ever recorded from an interstellar object, a milestone that elevates it from curiosity to historical significance. The trajectory itself is fascinating. Atlas came inbound almost parallel to the ecliptic plane, the flat disk where Earth and the other planets orbit. That is unusual. Random interstellar objects should approach from all directions, reflecting the three-dimensional structure of the galaxy. Objects from the galactic disk should cluster near the ecliptic, but objects from the halo, the diffuse cloud of stars surrounding the Milky Way, should approach from steep angles diving down from above or below the plane. Atlas's near-ecliptic approach suggests it might have originated from a star system whose orbital plane happens to align with ours, or it could be a statistical fluke, the kind of thing that happens when you only have 3 data points. With such a small sample size, every observation carries enormous weight and you can't yet distinguish patterns from noise. But let's talk about what makes this detection historically unique. Radio observations of comets aren't new. We've been studying hydroxyl emission and absorption from solar system comets since the 1960s using the same techniques that detected the signal from Atlas. What is new is the source, an object that formed around another star carrying ices and organics that assembled in an alien protoplanetary disk, now passing close enough to our Sun that we can analyze its chemistry in real time. This is direct sampling of extrasolar material without needing to send a probe to collect it. The comet came to us and all we had to do was point our telescopes at it and listen. Radio absorption studies provide a window into chemistry that other techniques can't match. Optical spectroscopy tells you about reflected sunlight, which depends on surface composition and geometry. Infrared observations reveal thermal emission, which tells you about temperature, but not necessarily chemistry. Ultraviolet spectroscopy can catch electronic transitions in molecules like O and carbon monoxide, but it is sensitive to solar contamination and atmospheric absorption. Radio spectroscopy, especially in the L band around 1.4 GHz, cuts through most of that noise. The hydroxyl lines are clear, unambiguous, and directly tied to water abundance. If you want to know how much water a comet contains, radio is often your best bet. And here is the thing, most interstellar objects pass completely unnoticed. They're faint, they're fast. They don't get close enough to the Sun to brighten significantly, or they approach from directions that put them in bad viewing geometry from Earth. The fact that we've only confirmed 3 in 8 years doesn't mean only 3 have passed through. It means only 3 have been bright enough, slow enough, and well-positioned enough for us to detect and characterize them before they vanished back into the dark. How many have we missed? Dozens, hundreds. The numbers depend on models of galactic stellar populations and planetary system architectures, but estimates suggest we should be detecting a handful per year with current survey capabilities. The fact that we're not tells you something about the challenges of interstellar object astronomy. You have to be looking at the right place at the right time, and even then you have to recognize what you are seeing before the object moves on. Now, speculate with me for a moment. What if these objects are part of a natural delivery system for organic compounds? Stars eject comets and asteroids all the time. Gravitational interactions during planet formation, scattering small bodies into interstellar space. Some estimates suggest the Milky Way contains trillions of rogue comets wandering between stars, too faint to see, but collectively representing an enormous reservoir of ice and organics. If even a tiny fraction of those objects contain prebiotic molecules, amino acids, nuclear bases, the chemical precursors to life, then interstellar space isn't empty. It is full of chemistry, slowly mixing, redistributing material between stellar systems on timescales of millions of years. Earth might have received its water and organics from exactly this kind of process. Interstellar visitors colliding with the young planet, depositing volatiles that eventually pooled into oceans and kick-started biology. That is the panspermia hypothesis in its most conservative form. Not that life itself travels between stars, but that life's ingredients do. and 3 Atlas with its hydroxyl signature confirming water breakdown and its trajectory proving extrasolar origin supports that idea. It is a data point, one of the first, showing that the chemistry necessary for life isn't confined to individual star systems. It moves, it spreads, and given enough time, given billions of years and countless collisions, it could seed habitable worlds throughout the galaxy. Which raises a question: if the ingredients for life are common and mobile, why is life itself seemingly rare? Or is it rare? Maybe we just don't know how to recognize it yet. Or maybe we're alone. Not because the chemistry is missing, but because the spark that transforms chemistry into biology is vanishingly unlikely. A statistical miracle that has happened only once in the observable universe. But I am getting ahead of the story. The immediate implication of the 3 Atlas detection is simpler. We can now study interstellar material using radio spectroscopy, adding a powerful new tool to the toolkit of planetary astronomy. The next visitor might be even richer in volatiles, closer, brighter, better positioned for multi-wavelength follow-up. We're entering an era where interstellar object science is transitioning from opportunistic observations to systematic study, and the chemical insights we gain will reshape our understanding of planetary system formation, not just here but everywhere. Because if Atlas carried water and organics across light years, then every other ejected comet does too, and the galaxy is crisscrossed with invisible highways of chemistry waiting to be mapped. Part 7, Chemistry, Physics, and the Volatile Budget of an Interstellar Object. So what exactly is happening inside 3I Atlas as it heats up? To understand the hydroxyl detection, you need to understand the physics of volatile sublimation, the process that transforms frozen ices directly into gas without passing through a liquid phase. It is the same process that makes dry ice, frozen carbon dioxide, smoke when you leave it out at room temperature. Heat flows into the solid, breaks the molecular bonds holding the crystal structure together, and molecules escape into the surrounding space. For water ice, this happens efficiently at temperatures above 170 Kelvin, but the rate increases exponentially as you warm up. At 230 Kelvin, the estimated surface temperature of Atlas at the time of the detection, water sublimation is vigorous, releasing gas at rates that can support a visible coma and tail. The Swift UV telescope confirmed those water sublimation signatures weeks before the radio detection. Swift specializes in ultraviolet spectroscopy, catching the electronic transitions of molecules as they fluoresce under solar radiation. Hydroxyl in particular has strong UV emission lines that appear when the molecules absorb sunlight and emit it at characteristic wavelengths. Swift saw those lines, measured their intensity, and calculated a water production rate on the order of 10 to the power of 27 molecules per second. That is a huge number, but it is actually modest for a comet near perihelion. Larger comets can release 10 to the power of 29 or even 10 to the power of 30 molecules per second at peak activity. Atlas is small, probably a few hundred meters across, so its volatile output is correspondingly limited, but it is enough to create a detectable hydroxyl cloud extending thousands of kilometers from the nucleus. Here is the process. Step by step, solar ultraviolet photons hit water molecules in the coma. The photons carry enough energy to break the oxygen-hydrogen bonds, splitting H2O into hydroxyl, O, and atomic hydrogen H. This is photodissociation, and it happens on time scales of hours to days depending on the intensity of the UV field. The hydrogen being light escapes quickly diffusing out of the coma and eventually merging with the solar wind. The hydroxyl sticks around longer with a lifetime of about 100,000 seconds before it either photodissociates further into oxygen and hydrogen or collides with other molecules. During that lifetime, the O molecules absorb radio at their characteristic frequencies, creating the absorption lines MeerKAT detected. The strength of those lines depends on the column density of hydroxyl along the line of sight, which in turn depends on the water production rate and the geometry of the observation. Compare this with TUI Borisov, which also showed hydroxyl emissions during its 2019 passage. Borisov's O lines were detected by multiple radio observatories, including the IRAM 30-meter telescope in Spain and the Nanai radio telescope in France. But Borisov's hydroxyl signal was weaker, indicating lower water production relative to Atlas. Despite Borisov being physically larger, why the difference? Composition. Not all comets are created equal. Some are richer in water ice, while others contain more carbon dioxide or carbon monoxide or exotic volatiles like methane and ammonia. Atlas appears to be unusually water-rich. either because it formed in a region of its parent protoplanetary disk where water ice was abundant, or because it lost other volatiles over millions of years of interstellar exposure, leaving water as the dominant remaining component. The thermal environment at 230 Kelvin is critical for understanding this. At that temperature, water ice sublimates readily, but more volatile species like carbon monoxide, which sublimates at temperatures as low as 30 Kelvin, are probably long gone. If Atlas has been drifting through interstellar space for millions of years, exposed to cosmic rays and the faint background radiation of the galaxy, any highly volatile ices on its surface would have sublimated slowly over time. What is left is primarily water ice, possibly mixed with refractory organics that don't sublimate easily, creating a dirty snowball that releases water preferentially as it heats up. This selective loss of volatiles is one reason interstellar comets might look different from solar system comets, even if they formed through similar processes. Now, let's talk about pressure and sublimation rates. Sublimation isn't just about temperature, it is about the balance between vapor pressure and ambient pressure. In the hard vacuum of space, the ambient pressure is essentially zero, which means even small amounts of heating can cause rapid sublimation. But if the gas releases fast enough, it creates its own local pressure, a thin atmosphere around the nucleus that can slow further sublimation. This self-regulation is why comets don't explode instantly when they approach the sun. The gas escaping from the surface forms a buffer layer that moderates the heating, allowing sublimation to proceed at a steady rate rather than all at once. For Atlas, the estimated gas production rate suggests the surface pressure in the coma is around 10 to the power of -6 millibars, a trillion times less than Earth's atmosphere, but enough to affect the thermal balance. Implications for planetary formation models are significant. If interstellar comets can retain water ice over timescales of millions of years, that tells you something about the stability of ices in the cold, dark conditions between stars. It suggests that volatile, rich bodies can survive ejection from their parent systems, maintain their chemical integrity during interstellar transit, and deliver those volatiles intact to any planetary system they happen to encounter. This supports models of planetary system formation that invoke late-stage volatile delivery, the idea that rocky planets like Earth might initially form dry and then acquire their water and organics through comet impacts during the final stages of accretion. If interstellar comets can contribute to this process, delivering extrasolar water to young planets, then the chemistry of any given world might be a mix of local and imported material, blurred by billions of years of cosmic traffic. And this brings us back to panspermia, one of the oldest and most controversial ideas in astrobiology. The term literally means seeds everywhere, and it proposes that life, or at least life's precursors, might spread between planets or even between star systems via comets and asteroids. The conservative version, sometimes called pseudopanspermia, suggests that organic molecules, the building blocks of life, travel on these objects and seed sterile worlds with the chemistry needed for biology to emerge independently. The radical version suggests that life itself, microorganisms in a dormant state, could survive the journey and colonize new planets. Most scientists are skeptical of the radical version because space is hostile. Radiation, vacuum, extreme temperatures, all working against the survival of even hardy microbes. But the conservative version is entirely plausible. Organic molecules are tough. They can survive radiation doses that would sterilize a planet's surface, and experiments have shown that amino acids and nucleobases, key components of proteins and DNA, can form in icy mantles under the kind of radiation conditions you'd find in interstellar space. Laboratory analogues have tested this directly. Researchers take mixtures of water ice, methanol, ammonia, and carbon monoxide, freeze them onto surfaces at temperatures around 10 Kelvin, and bombard them with ultraviolet light or high-energy particles to simulate cosmic rays. The result, complex organic chemistry, including the formation of amino acids like glycine and alanine, the simplest building blocks of proteins. If this chemistry happens in the lab, it almost certainly happens in space on the surfaces of comets and dust grains, drifting through molecular clouds, which means every interstellar object like Atlas is potentially carrying a library of prebiotic molecules, a chemical toolkit for kickstarting biology on any world where conditions are right. The detection of hydroxyl from Atlas confirms that even interstellar material that has been wandering the galaxy for who knows how long, can retain complex molecules. Water doesn't just survive interstellar transit, it survives intact enough to sublimate and produce detectable chemical signatures when heated. That is profound. It means the chemical inventory of the cosmos isn't static, locked into individual star systems. It is dynamic, constantly redistributed by gravitational interactions and stellar encounters with comets and asteroids, acting as delivery vehicles. Life's ingredients aren't rare or special, they're common, mobile, and probably distributed throughout the galaxy, on countless icy bodies we'll never see. Atlas just happens to be one we caught in the act. Part 8, Trajectory Oddities and the Maneuvering Hypothesis. Now, let's talk about the orbit itself, because if the chemistry of 3 Atlas raises questions, the trajectory adds fuel to the speculation fire. The object's path through the solar system is hyperbolic as expected for an interstellar visitor, but the specific geometry is unusual enough to warrant attention. Atlas approached almost exactly along the ecliptic plane, the flat disk defined by Earth's orbit around the Sun. Most solar system bodies cluster near this plane because they formed from the same rotating disk of gas and dust that collapsed to create the Sun and planets 4.6 billion years ago. But interstellar objects didn't form here. They should arrive from random directions reflecting the three-dimensional distribution of stars in the galaxy. Yet Atlas came in flat as if it were deliberately targeting the inner solar system, where planets are densely packed. NASA's anomaly report, compiled from observations spanning September through October, noted minor deviations in the predicted trajectory, variations small enough that they could be explained by asymmetric outgassing. When a comet releases gas, that gas carries momentum. If the outgassing is stronger on one side of the nucleus than the other, perhaps because one hemisphere is more volatile, rich or more directly illuminated, the result is a net thrust that pushes the comet slightly off its expected path. This is called a non-gravitational force, and it is well documented for solar system comets. Halley's Comet, for instance, returns to the inner solar system a few days earlier or later than purely gravitational calculations predict because rocket effects from sublimation push it along or slow it down depending on how the nucleus is oriented. But some observers have claimed the deviations in Atlas's orbit look too systematic, too coordinated to be random outgassing. They point to the tail and anti-tail formations as evidence of controlled thrust, symmetrical jets firing in opposite directions that would allow for precise trajectory adjustments. The New York Post, never one to shy from sensational coverage, ran articles about the comet maneuvering through the solar system, complete with artist renditions of a sleek probe wrapped in ice. The claim is that if you wanted to build an interstellar spacecraft but avoid detection, you'd cloak it in cometary material, use the sublimation as thrust, and navigate using precisely controlled gas jets. From a distance, it would look like a comet. Only detailed analysis of the trajectory would reveal the truth. Let's be clear, this is speculative to the point of fantasy, but it is not entirely baseless. The physics of using outgassing for propulsion is sound. In fact, proposals for interstellar probes have suggested exactly this approach. Coat a spacecraft in frozen hydrogen or water. Let solar heating sublimate the ice and use the expanding gas as a propellant. It is inefficient compared to chemical rockets or ion drives. But it is simple, requires no onboard power, and makes the spacecraft indistinguishable from a natural comet until someone looks closely at the trajectory. The Breakthrough Starshot project, which aims to send tiny laser-propelled probes to Alpha Centauri, has explored hybrid designs that combine light sails with volatile coatings for exactly this reason. The anti-tail formation adds complexity. Anti-tails can appear naturally as perspective effects, but the symmetry observed in Atlas is striking. The main tail and anti-tail appeared roughly equal in brightness and length, suggesting that dust was being ejected in two opposite directions with similar force. That is hard to explain with simple rotational outgassing, unless the nucleus has active regions at opposite poles firing jets aligned with the rotation axis. If the nucleus spins fast enough and the polar aligned jets are strong enough, you'd get exactly this kind of symmetry. But that requires a specific configuration, active areas at both poles, which isn't guaranteed by any model of cometary structure. Timing adds another layer of intrigue. Atlas reached perihelion on October 29, 2025, at a distance of about 0.66 astronomical units from the Sun, roughly 2/3 the distance between Earth and the Sunday. That is close enough for significant solar heating, but not so close that the comet would be torn apart by tidal forces. More interestingly, perihelion occurred near what orbital mechanics people call an Oberth maneuver window, the point in an orbit where a small change in velocity has the maximum effect on the final trajectory. If you wanted to adjust your path to target a specific destination after leaving the solar system, perihelion would be the optimal place to do it. You'd wait until you are moving fastest deep in the Sun's gravity. Well, Then apply thrust to change your direction with maximum efficiency. The fact that Atlas passed through this window with trajectory deviations, however small, has fueled speculation that something guided or is guiding its path. But let's apply some healthy skepticism. Thermal models of cometary outgassing can explain trajectory deviations without invoking propulsion. When one side of a comet heats up faster than the other, perhaps because its rotation axis is tilted relative to the Sun, that side sublimates more gas, creating thrust. The result is a torque that can spin the nucleus up or slow it down, and a force that nudges the trajectory slightly. These effects are small but measurable, and they've been observed on every well-studied comet in our solar system. There is no direct evidence of propulsion systems, no anomalous accelerations that can't be explained by standard physics, no spectroscopic signatures of exotic chemistry that would suggest artificial outgassing control. And yet the question lingers: if it were artificial, how would we know? If an advanced civilization wanted to send probes into other star systems, and if they were smart about it, those probes would look like natural objects. They'd use gravity assists, solar flybys, and chemical releases that mimic cometary behavior. The only giveaway might be statistical trajectories that cluster around certain types of stars, perihelion distances that optimize observational geometry, chemical signatures too consistent or too precisely timed to be natural with a sample size of 3 confirmed interstellar objects. We're nowhere near being able to detect such patterns. We need hundreds, thousands of detections before we could distinguish between natural visitors and hypothetical probes disguised as comets. So here is where we land on the maneuvering hypothesis. Possible in principle, unsupported by current evidence, and almost certainly unnecessary to explain the observations. Atlas is behaving oddly. Yes, but comets are intrinsically chaotic objects. Their rotation states, thermal properties, and outgassing patterns depend on internal structure we can't directly observe. Small inhomogeneities in composition can produce large variations in behavior. The trajectory deviations are real, but within the range of what asymmetric outgassing can produce. The perihelion timing near an Oberth window is coincidental, because every orbit has a perihelion and every perihelion is theoretically optimal for trajectory changes. If you look for patterns with a small sample size, you'll find them whether they mean anything or not. But I'll leave you with this thought. What if coincidences aren't random? What if the universe in its vast complexity sometimes produces patterns that look designed even when they're not? And what if buried in those patterns, there is information we haven't learned to read yet? Because whether Atlas is maneuvering or just tumbling through space according to the impersonal laws of physics, its trajectory has delivered it to us. Close enough to study, bright enough to detect, timed perfectly to produce a radio signature that made history. Coincidence or choreography? The data doesn't answer that question. Not yet. Part 9 SETI. Radio telescopes and a new detection frontier. Traditional SETI. The search for extraterrestrial intelligence has always focused on one thing: narrowband beacons. The logic is straightforward. Natural astrophysical sources emit radiation across a broad range of frequencies. Stars radiate across the electromagnetic spectrum from gamma rays to radio. Pulsars produce broadband pulses. Supernova remnants glow in every wavelength simultaneously. But a deliberate transmission from an intelligent civilization would be different. It would be spectrally pure, concentrated at a single frequency or a narrow band of frequencies, because that is the most efficient way to pack information into limited power. If you are broadcasting across the galaxy and you want your signal to be detectable, you don't waste energy spreading it across the spectrum. You pick a frequency, probably something significant like the hydrogen line at 1420.406 MHz, and you pump all your power into that channel. The result is a spike in the spectrum, a needle so sharp it can't be confused with natural phenomena. That is what SETI searches for. Giant radio telescopes like the Green Bank Telescope in West Virginia, the 500-meter aperture spherical telescope FASTS in China, and the Very Large Array in New Mexico spend thousands of hours scanning the sky, looking for narrow band signals that repeat, that show structure, that carry the unmistakable fingerprint of intentionality. They've been doing this since Frank Drake's Project Ozma in 1960, when he pointed a radio dish at Tau Ceti in Epsilon Eridani and listened for 6 months. He heard nothing. 65 years later, despite improvements in sensitivity that would have seemed miraculous to Drake, we're still hearing nothing. No repeating beacons, no modulated transmissions, no alien encyclopedia beamed our way, just the vast noisy silence of the cosmos. The hydroxyl detection from 3 Atlas forces a paradigm shift in how we think about technosignatures. What if we've been looking for the wrong kind of signal all along? What if intelligence doesn't always broadcast intentionally? What if the signatures of advanced technology are subtle, embedded in chemistry or orbital dynamics, indistinguishable from natural processes unless you know exactly what to look for? This is the concept of non-intentional technosignatures, industrial byproducts or engineering artifacts that leak detectable radiation, not because anyone wants them to, but because they're the inevitable consequence of technology operating at scale. Think about Earth as an example. We've been leaking radio signals into space for over a century. Ever since Marconi sent his first wireless transmission, television broadcasts, radar installations, satellite communications, all of it radiating outward at the speed of light, creating an expanding bubble of electromagnetic noise that currently extends about 100 light-years in every direction. If an alien civilization pointed a sensitive radio telescope at our solar system from a nearby star, they wouldn't necessarily see a deliberate beacon. They'd see chaos, thousands of overlapping frequencies modulated in ways that reflect our technology, our entertainment, our military communications. It would be messy, but it would be unmistakably artificial. That is a non-intentional technosignature. And it is probably far more common than deliberate SETI beacons, if only because most civilizations probably aren't trying to announce their presence to the galaxy. Now, apply that logic to chemistry. An advanced civilization capable of building starships or manipulating comets would inevitably leave chemical signatures. Engine exhaust if they use propulsion, unusual isotopic ratios if they're refining materials or using nuclear reactions, molecular abundances that don't match equilibrium chemistry if they're actively controlling outgassing or atmospheric composition. These wouldn't be messages. They'd be fingerprints, traces left behind by technology operating in environments we can observe, and the only way to detect them is through spectroscopy, the same technique we use to find hydroxyl in 3 Atlas. MeerKAT is uniquely positioned to pioneer this kind of detection. The array's 64 dishes spread across 8 kilometers of the Karoo Desert in South Africa create an interferometer with extraordinary sensitivity in the L-band. The radio frequency range from 1 to 2 gigahertz. That is where hydroxyl lives along with dozens of other molecules important for astrochemistry. MeerKAT can simultaneously observe multiple frequency channels, searching for emission and absorption lines from water, carbon monoxide, formaldehyde, methanol, all the complex organics that appear in star-forming regions and apparently on interstellar comets. The correlator, the supercomputer that combines signals from all 64 dishes, can process petabytes of data per Dalton UI, flagging interesting spectral features in near real time, filtering out Earth-based interference is critical, and MeerKAT excels at it. The Karoo is one of the most radio-quiet regions on the planet, protected by South African law from radio frequency pollution. No cell towers, no Wi-Fi routers, no broadcast stations within hundreds of kilometers. The few sources of interference that do exist, satellites passing overhead or distant radar installations, have known frequencies and can be flagged and removed during data processing. The hydroxyl detection from Atlas passed every interference check. The signal appeared only when the telescope was pointed at the comet's predicted position. It tracked with the object's motion across the sky. It Doppler shifted by exactly the amount the velocity measurements required, and it disappeared when the observation window closed, consistent with the comet moving behind the Sun from Earth's perspective. This adds enormous credibility to the detection. Systematics. The systematic errors that plague any scientific measurement are the bane of radio astronomy. Sidelobe leakage, where the telescope picks up signals from directions other than where it is pointed, can create false detections. Atmospheric absorption, particularly from water vapor in Earth's atmosphere, can distort spectra and create artificial features. Calibration errors, if the instrument isn't properly tuned, can introduce noise that looks like signal. MeerKAT's data integrity checks are designed to catch all of these, and the Atlas detection passed every test. The hydroxyl lines appeared with the correct shape, the correct frequency, the correct intensity. This wasn't an artifact, it was real. Efforts to replicate the detection are ongoing. The Green Bank Telescope, a 100-meter single-dish instrument in West Virginia, is one of the most sensitive radio telescopes on Earth, capable of detecting signals far weaker than MeerKAT's threshold. FAST, the 500-meter dish in China, has even greater collecting area and could potentially pick up hydroxyl lines from Atlas if the geometry allowed observation. The Very Large Array in New Mexico, with its 27 dishes spread across the desert, offers a different kind of sensitivity. better at filtering out point sources and isolating extended emission from a comet's coma. If all three independently confirm the hydroxyl signature, that would remove any lingering doubt about the detection's reality. But here is the complication. 3I Atlas is variable. The two earlier observation attempts on September 20th and 28th detected nothing. No hydroxyl, no other molecular lines, just noise. That tells you the signal is transient, appearing only when conditions are right. Maybe the comet needs to reach a certain temperature threshold before water sublimation becomes strong enough to produce detectable hydroxyl. Maybe the viewing geometry matters with hydroxyl clouds, concentrated in certain directions relative to the nucleus. Maybe the rotation of the nucleus brings volatile, rich regions into sunlight, periodically creating bursts of outgassing that fade when those regions rotate back into shadow. Without continuous monitoring, it is impossible to say. And this raises a deeper question that cuts to the core of SETI philosophy. If alien technology mimics natural chemistry, how would we ever distinguish them? Suppose an advanced civilization has mastered nanotechnology, building machines at the molecular level that can control chemical reactions with atomic precision. They could synthesize molecules, release them in specific patterns, create spectral signatures that look completely natural but encode information in subtle ways. Ratios of isotopes, timing of release events, correlations between different molecular species, unless you knew exactly what to look for. Unless you had a library of natural spectra to compare against an algorithm sophisticated enough to detect statistical anomalies, you'd never know. The signal would hide in plain sight, camouflaged as chemistry. This is the problem with techno-signatures in the 21st century. We're getting better at detecting subtle signals, building instruments sensitive enough to see individual molecules on comets millions of kilometers away. But our ability to interpret those signals to distinguish between natural complexity and engineered patterns lags far behind. We need larger sample sizes, more detections, machine learning algorithms trained on databases of natural and hypothetical artificial spectra. We need to stop thinking of SETI as a binary problem. Either we detect a beacon or we don't, and start thinking of it as a continuum. A spectrum of signals ranging from obviously natural to ambiguously structured to unmistakably artificial. 3 Atlas falls somewhere in the middle of that spectrum. Natural enough to explain with standard physics, but unusual enough to make you wonder. So here is where we are. MeerKAT detected hydroxyl from an interstellar comet, a first in the history of radio astronomy. The signal is consistent with natural chemistry, water breakdown under solar heating. But it is also evidence that we can now probe the composition of extrasolar material in real time using techniques that could potentially detect non-intentional technosignatures if they exist. The next interstellar visitor might be richer in complex organics, producing a spectrum with dozens of molecular lines. Or it might show isotopic ratios that don't match stellar nucleosynthesis models. Or it might release gases in patterns too regular to be thermal chaos. We won't know until we look. And we won't look unless we build the instruments and develop the analytical framework to interpret what we find. Because even if it is natural, even if every interstellar object we ever detect turns out to be just a comet, the implications remain extraordinary. The universe is full of chemistry, and we're finally learning to listen. Part 10, Broader Implications, Life, Technology, and Interstellar Visitors. Let's step back and ask the philosophical question that underlies all of this. What if nature and intelligence overlap more than we've ever allowed ourselves to believe? We've spent centuries constructing a conceptual wall between the natural and the artificial, between processes governed by physics and chemistry versus those driven by intent and design. But maybe that wall is an illusion, a cognitive artifact of our limited perspective. Maybe intelligence isn't separate from nature, but an emergent property of it. One manifestation of the universe's tendency to organize itself into increasingly complex structures. And if that is true, then the distinction between a natural comet and a hypothetical artificial probe becomes less clear because both are expressions of the same underlying physical laws. If the hydroxyl detection from 3I Atlas is natural, and it almost certainly is, then what we're seeing is proof that interstellar ices can carry the building blocks of life across light years of empty space. Water, the universal solvent, the molecule that makes Earth's oceans and your blood, and every living cell on this planet possible, exists in abundance on objects born in other star systems. It freezes onto dust grains in protoplanetary disks, gets incorporated into comets and asteroids during planet formation, and sometimes gets ejected when gravitational interactions fling those objects into interstellar space. Once ejected, these icy bodies drift for millions of years, maybe billions, exposed to cosmic rays and starlight, but cold enough that the volatiles remain frozen. And if they happen to encounter another star system, if gravity pulls them inward, they heat up, release those volatiles, and deliver their cargo of water and organics to whatever worlds happen to be there. This is panspermia in its most defensible form, not the radical claim that living organisms travel between stars, but the conservative claim that chemistry does. Life requires certain ingredients: liquid water, organic molecules, energy sources. The first two can be delivered by comets. The third exists on any planet close enough to a star to maintain liquid water on its surface. Put those three together in the right environment and biology might emerge. Not because some external force planted it there, but because chemistry, given enough time and the right conditions, tends toward complexity. Amino acids form spontaneously in certain environments. Lipid membranes self-assemble. RNA molecules can catalyze their own replication. Life might not be a miracle. It might be an inevitability, a predictable outcome of chemistry playing out on planetary surfaces where conditions permit. But if that is true, why does the galaxy seem so quiet? This is the Fermi paradox. The discrepancy between the high probability of extraterrestrial civilizations based on the sheer number of stars and planets and the complete absence of evidence for them. If life's ingredients are common, and chemistry tends toward complexity, you'd expect biology to emerge on countless worlds. And if biology is common, intelligence should emerge sometimes. Maybe rarely, but with hundreds of billions of stars in the Milky Way alone, even a tiny fraction should yield millions of technological civilizations. But where are they? Why haven't we seen their signals, their megastructures, their probes exploring the galaxy? Maybe the answer is simpler than we think. Maybe intelligence is common, but communication across interstellar distances is so difficult, so energy-intensive that most civilizations don't bother. Maybe they're out there living on their worlds, building their societies, but they're not broadcasting, because there is no reason to. Or maybe intelligence is common but short-lived. Civilizations rising and falling on timescales of thousands of years, brief flickers in cosmic time that rarely overlap. Or maybe we're looking in the wrong way, searching for radio beacons when the real signals are encoded in chemistry, orbital mechanics, or phenomena we don't even have names for yet. Or maybe, and this is the possibility that keeps astrobiologists awake at night, maybe Earth is unique, maybe the chemistry is common, but the spark isn't. Maybe life's emergence requires not just the right ingredients, but an improbable chain of events. The right planet at the right distance from the right kind of star with a large moon to stabilize its rotation with plate tectonics, to recycle carbon with a magnetic field to shield against radiation with a Jupiter-sized planet in the outer system to deflect comets and asteroids. Stack enough conditions together, each individually probable but collectively rare, and you get a filter, something that explains why life exists here but nowhere else we can detect. But let's return to 3 Atlas and what it teaches us. The hydroxyl detection, regardless of whether it is natural or hypothetical artificial, proves that we can study the chemical composition of extrasolar material using spectroscopy. This is a revolution in planetary science. Before this, everything we knew about planets and comets beyond our solar system came from indirect methods. Transit spectroscopy of exoplanet atmospheres, infrared observations of dusty disks, computer simulations extrapolating from what we know locally. But Atlas brought us a sample, not physically, but close enough that our instruments could analyze its volatiles in real time. That is direct sampling without needing a spacecraft. And it opens up possibilities we're only beginning to explore. Connecting this to broader missions, the James Webb Space Telescope, JWST, is revolutionizing exoplanet science by mapping atmospheric compositions with unprecedented detail. The Vera C. Rubin Observatory, which we'll discuss later, will discover interstellar objects months before they reach perihelion, giving us time to coordinate multi-wavelength observations. Missions like JWST Rubin and radio arrays like MeerKAT and ALMA form a network of instruments that together can dissect the chemistry of the cosmos at every scale, from individual molecules on comet nuclei to atmospheric composition on planets hundreds of light years away. Each detection refines our sense of how common life's ingredients are, and the answer increasingly seems to be everywhere. Water has been detected on exoplanets, in protoplanetary disks, in the atmospheres of hot Jupiters, in the icy moons of our own solar system. Organic molecules, complex carbon-based compounds including amino acids, have been found in meteorites, in interstellar clouds, in the comets. The building blocks are common, Chemistry is universal. The laws of physics and thermodynamics operate the same way everywhere. If you create the right conditions, liquid water in contact with organic molecules and an energy source, chemistry starts doing interesting things. It polymerizes, it forms structures. It begins, however, tentatively, the long journey toward what we might call life. And here is the chilling thought. Maybe intelligence isn't trying to talk to us because it is already here, distributed throughout the galaxy in a form we don't recognize. Not alien civilizations broadcasting from distant planets, but chemistry itself. Self-organizing patterns embedded in comets and asteroids that carry information across interstellar distances in ways we're only beginning to understand. Maybe the messages aren't encoded in radio waves, but in isotopic ratios, in molecular abundances, in the very structure of the objects passing through our solar system. Maybe 3 Atlas is a message not from intelligent beings, but from the cosmos itself, telling us that life's ingredients are everywhere, constantly redistributed, written into the fabric of the galaxy. That idea edges into territory that makes scientists uncomfortable. The notion that the universe has something like intentionality, that chemistry and biology aren't random but directed by some deeper organizing principle. Most researchers would just reject that outright. Physics is physics. Chemistry is chemistry. Emergent complexity doesn't require a designer, but it is worth sitting with the discomfort, because the alternative, that we're alone in a vast, cold, indifferent universe, is its own kind of cosmic horror. Maybe the truth is somewhere in between. Maybe the universe isn't trying to communicate, but it is full of information, nonetheless. Patterns waiting to be decoded by anyone smart enough to look. Part 11, Quasi-Lunar Moon 2025, PN7 Earth's Tilted Companion. While 3 Atlas grabbed headlines with its interstellar chemistry, another discovery was quietly reshaping our understanding of near-Earth space. In August 2020, 5 astronomers confirmed the existence of 2025 PN7, a small asteroid following a bizarre tilted orbit that keeps it loosely bound to Earth's gravitational influence. It is what is called a quasi-satellite, a class of object that orbits the Sun but appears from Earth's perspective to orbit our planet. The gravitational dance is complex, a 3-body problem involving the Sun, Earth, and the asteroid, resulting in a trajectory that loops around Earth without ever being truly captured. Quasi-satellites are rare, but not unprecedented. Earth has several known quasi-satellites at any given time. Small rocky bodies, typically a few dozen meters across, that get temporarily trapped in resonant orbits. They stick around for decades or centuries before perturbations from other planets knock them out of their loops and send them wandering elsewhere in the solar system. What makes 2025 PN7 special is its orbital inclination, tilted about 40 degrees relative to Earth's orbital plane. Most quasi-satellites have low inclinations circling near the ecliptic, where gravitational interactions with Earth are strongest. PN7's steep tilt suggests it arrived from an unusual angle, possibly from the main asteroid belt after a close encounter with Mars or Jupiter perturbed its orbit. The discovery highlights just how dynamic near-Earth space actually is. We tend to think of the Moon as Earth's only companion, but the reality is more complicated. There is a whole population of small bodies gravitationally associated with our planet, some captured temporarily like PN7, others co-orbiting at stable Lagrange points where gravitational forces balance. The Trojan asteroids at Earth's L4 and L5 points, discovered only in the past 2 decades, are another example. These populations change constantly, with objects drifting in and out on timescales of years to millennia. What looks like empty space is actually a bustling neighborhood of rocks, each following its own complex path through the gravitational landscape. Tie this back to 3I Atlas. Unexpected celestial behavior is more common than we think. We're used to the predictability of the solar system, planets following Keplerian orbits that can be calculated centuries in advance. But introduce small bodies, perturbations, non-gravitational forces, and the system becomes chaotic. Comets change brightness unpredictably. Asteroids tumble erratically. Quasi-satellites loop around Earth in patterns so complex they require numerical integration to model. And every so often, an interstellar visitor comes screaming through, following a trajectory that originates outside the system entirely. The universe is messy, and the more carefully we look, the more surprises we find. 2025 PN7's detection showcases improvements in survey technology. The Atlas system, Asteroid Terrestrial Impact Last Alert System, uses multiple wide-field telescopes to scan the sky nightly, searching for moving objects that might pose a collision risk. It is designed to catch asteroids on Earth-crossing orbits, but it inevitably discovers other things too. Distant comets, quasi-satellites, interstellar objects like 3 Atlas. As survey technology improves, as telescopes get larger and detectors more sensitive, the discovery rate accelerates. We're finding hundreds of new asteroids every month, and each one adds to our understanding of the solar system's small body populations. Here is a fun fact. Quasi-satellites can remain gravitationally linked to Earth for decades, sometimes centuries, following orbits so convoluted they look like tangled knots when you plot them in 3 dimensions. PN7 will probably stick around for 50 to 100 years before perturbations nudge it out of resonance, and it drifts away. During that time, it'll loop around Earth multiple times per year, always staying about 20 million kilometers away, never getting close enough to be captured into a true orbit, but never wandering far enough to break free entirely. It is a cosmic ballet choreographed by gravity, and it happens without anyone noticing unless astronomers happen to point a telescope in the right direction at the right time. And here is where the speculation gets fun. What if something hid among them watching? Quasi-satellites are perfect for long-duration observation of Earth. They're stable enough to loiter for decades, but far enough away that they wouldn't be obvious. A hypothetical probe disguised as a small asteroid could sit in a quasi-satellite orbit, passively observing our planet, recording electromagnetic emissions, mapping atmospheric composition, all while appearing completely natural. We wouldn't notice unless we looked closely, and even then, we'd probably classify it as just another rock. The idea sounds paranoid, but it is not entirely implausible. If you wanted to study an inhabited planet without revealing your presence, parking a probe in a quasi-satellite orbit would be a clever strategy. Upcoming observations will confirm PN7's origin, whether it is a captured asteroid from the main belt or, intriguingly, a fragment of an interstellar wanderer. Spectroscopy can determine its composition, revealing whether it is made of ordinary silicate rock or something more exotic. Photometric measurements can track its rotation and search for signs of internal structure. If it turns out to be unusual in any way, chemically or physically, that would add another layer to the mystery. But most likely it is just a rock, an unremarkable chunk of stone that happened to drift into a resonant orbit with Earth for a while before moving on. Still, the fact that we can find these objects, characterize them, and track their orbits shows how far our observational capabilities have come. This ties into the broader theme. Space is full of surprises waiting at the edge of detection. Every improvement in telescope sensitivity, every new survey that scans the sky more thoroughly reveals phenomena we didn't know existed. Quasi-satellites, interstellar comets, Trojan asteroids at Earth's Lagrange points, objects in retrograde orbits. The solar system is more complex, more dynamic, more interesting than mid-20th century textbooks suggested. And if our own stellar neighborhood is this full of unexpected discoveries, imagine what is waiting in the wider galaxy. Too faint or too distant for current instruments, but just within reach of the next generation. Part 12, Next-Gen Survey Instruments. ESO's foremost goes online. October 2025 brought another milestone. The European Southern Observatory's foremost telescope completed commissioning and began science operations. Foremost stands for 4-meter multi-object spectroscopic telescope, and the name undersells what this instrument actually does. It is not just a telescope, it is a spectroscopic surveying machine capable of observing 2,400 objects simultaneously, taking spectra from everyone and churning through millions of targets over its operational lifetime. If you want to build a chemical atlas of the Milky Way, if you want to classify every comet and asteroid in the inner solar system, if you want to understand galactic evolution by measuring the composition of millions of stars, Foremost is the tool for the job. The technology is straightforward but powerful. A 4-meter primary mirror collects light, and an array of robotic fiber positioners directs that light from individual targets into spectrographs. Each fiber, about the width of a human hair, can be positioned anywhere in the telescope's field of view, creating a switchboard that routes light from thousands of objects into instruments that split it into spectra. Those spectra reveal chemical composition, temperature, velocity, all the physical information encoded in starlight or the reflected sunlight from a comet. And because the system is automated, moving from target to target without human intervention, it can cover huge swaths of sky in a single night. Foremost data will help classify small bodies in the solar system, distinguishing between different asteroid taxonomies, identifying comets masquerading as asteroids, catching interstellar visitors before they reach perihelion. The chemical compositions Foremost measures will feed into models of planetary formation, refining our understanding of how volatiles like water and carbon get distributed during the chaotic early phases of system assembly. If 3 Atlas returned on a different trajectory, passing through foremost survey footprint, the telescope would capture its spectrum automatically, flagging it as an interstellar object based on velocity and composition within hours of detection. Connect this to interstellar detection, how next-gen instruments could spot objects like 3I Atlas earlier, giving more time for follow-up observations. MeerKAT detected hydroxyl from Atlas only during a narrow window when geometry and chemistry aligned. But if we'd known about Atlas months earlier, if optical surveys had caught it while it was still in the outer solar system, radio astronomers could have planned observations in advance, tracked the onset of volatile release, measured how hydroxyl production increased as the comet approached the Sun. Early detection transforms interstellar object science from opportunistic snapshots to systematic campaigns, and instruments like Foremost are key to making that happen. Europe and South Africa's facilities are networked for rapid response. When Foremost or another optical telescope identifies an unusual object, the detection triggers alerts sent automatically to radio observatories like MeerKAT. Infrared telescopes like the Very Large Telescope and space-based platforms like JWST. Within hours, multiple instruments can start observing, building a multi-wavelength picture of the object before it fades or moves out of observing range. This kind of coordination, impossible 20 years ago, is now routine, enabled by shared databases, standardized alert formats, and international collaborations that span continents and organizations. Foremost's role in building chemical atlases of the Milky Way extends beyond the solar system. The telescope will measure spectra from millions of stars, tracking how chemical composition varies with stellar age, location in the galaxy, and kinematic properties. Over time, these measurements will reveal the galaxy's formation history, showing how gas collapsed into stars, how supernova enriched the interstellar medium with heavy elements, how stellar migration redistributed those elements across thousands of light years. It's galactic archaeology, using chemistry to reconstruct events that happened billions of years ago. And here is a speculative thought. What if the next strange signal isn't from a visitor like 3I Atlas, but from our own galaxy's core? The galactic center is a chaotic place, a supermassive black hole surrounded by dense star clusters, molecular clouds and magnetic fields, strong enough to accelerate particles to relativistic speeds. Radio observations have revealed bizarre filaments, mysterious bubbles and transient events that defy easy explanation. Foremost could catch the optical counterparts to those radio signals, matching spectral features to physical processes, identifying molecules in environments we can barely imagine. Maybe the universe is broadcasting constantly, not from alien civilizations, but from the galaxy itself, and we're finally building instruments sensitive enough to translate the message. Compare Foremost to MeerKAT's niche, radio versus optical complementarity. Radio telescopes see molecules, the chemistry of gas and dust. Optical telescopes see atoms, the physics of stars and reflected sunlight. Infrared telescopes see heat, the thermal glow of planets and dust clouds. Ultraviolet telescopes see high-energy processes, shocks and radiation from hot stars. Each wavelength reveals a different aspect of reality, and only by combining them do you get the complete picture. The hydroxyl lines from 3 Atlas tell you about water chemistry. Optical spectra tell you about dust composition and surface reflectance. Infrared data tell you about temperature and volatile sublimation rates. Put it all together, and you understand not just what the object is, but where it came from and how it evolved. Large-scale survey synergy is the future of cosmic discovery. No single telescope, no matter how powerful, can answer every question. You need networks of instruments operating across the spectrum, coordinated by automated alert systems, feeding data into shared archives that researchers worldwide can access. That is the paradigm shift happening now. The transition from heroic solo observations to collaborative campaigns that leverage the strength of dozens of facilities simultaneously. And the discoveries are accelerating because of it. More interstellar objects, more exoplanets, more transient events, more chemical maps of star-forming regions, all appearing in databases faster than any individual scientist can keep up with. Part 13 Dark Matter. Hints in pulsar heartbeat patterns. Now we shift gears from interstellar visitors to something stranger, anomalies in the fabric of spacetime itself. Throughout 2025, pulsar timing arrays, networks of radio telescopes monitoring dozens of millisecond pulsars scattered across the galaxy, have been reporting something odd. The pulsars, those cosmic clocks that spin hundreds of times per second and beam radio pulses toward Earth with metronomic precision, aren't quite as regular as they should be. The deviations are tiny. Nanoseconds of variations spread across months of observation, but they're statistically significant. And more importantly, they're correlated. When one pulsar's timing shifts, others shift in a pattern that suggests something is stretching and squeezing the space between us and them. Pulsars are the collapsed cores of massive stars that exploded as supernova, neutron stars so dense that a teaspoon of their material would outweigh Mount Everest. They spin rapidly, often hundreds of times per second, and their magnetic fields are so strong they channel radiation into narrow beams that sweep across space like lighthouse beacons. If Earth happens to lie in the path of one of those beams, we see a pulse every time the neutron star rotates, and because the rotation is incredibly stable, pulsars function as natural clocks, some of them more precise than atomic clocks on Earth. Pulsar timing arrays use this property to search for gravitational waves, ripples in spacetime predicted by Einstein's general relativity. When a gravitational wave passes through the galaxy, it stretches space in one direction and compresses it in another, changing the distances between Earth and distant pulsars by tiny amounts. Those distance changes show up as timing variations. Pulses arrive slightly earlier or later than expected, depending on whether the gravitational wave stretched or compressed the space the light traveled through. By monitoring dozens of pulsars simultaneously, astronomers can detect the signature pattern of gravitational waves, correlations that distinguish real spacetime distortions from random noise, and that is exactly what pulsar timing arrays have been seeing. A correlated signal that looks like ultra-low frequency gravitational waves, oscillations with periods of years to decades, far longer than the millisecond period waves detected by LIGO and Virgo. The leading explanation is supermassive black hole binaries, pairs of black holes, each millions or billions of times the mass of the Sun, spiraling toward merger in the cores of distant galaxies. As they orbit each other, they stir spacetime like spoons in honey, generating gravitational waves that propagate outward at light speed. By the time those waves reach Earth, they're incredibly weak, barely perturbing the fabric of space. But pulsar timing arrays can detect them. But here is where it gets speculative. Some theorists propose the signal might not be gravitational waves from black holes. It could be dark matter, not the cold, non-interacting particles most models favor, but something more exotic. Oscillating fields or topological defects in spacetime left over from the early universe. Dark matter dominates the mass of the galaxy, outweighing ordinary matter 5-1. Yet we've never directly detected it. Every experiment designed to catch dark matter particles has come up empty. Maybe dark matter isn't particles at all. Maybe it is waves, fluctuations in some field we don't understand. And those fluctuations interact with space-time in ways that produce apparent gravitational wave signatures. This connects metaphorically to the idea that the cosmos literally pulses, that there is a rhythm underlying reality itself. Pulsars spin, black holes orbit, gravitational waves oscillate. Even the expansion of the universe accelerates and decelerates depending on the balance between matter and dark energy. Everything in the cosmos seems to follow cycles, repeating patterns that emerge from the underlying physics. And maybe those patterns constitute a form of communication, not intentional but informative, broadcasting the structure of reality to anyone capable of measuring them. Highlight parallels. Both pulsar timing and hydroxyl absorption rely on precise frequency analysis. In pulsar timing, you measure the frequency of radio pulses, tracking nanosecond variations over months. In spectroscopy, you measure the frequency of light absorbed or emitted by molecules, identifying chemical species from sub-megahertz line widths. Both techniques push measurement precision to absurd limits, extracting information from signals so faint they're barely above noise, and both reveal phenomena that would be invisible without those precise measurements. Gravitational waves in one case, molecular abundances in the other. Now speculate, could interstellar objects be responding to galactic-scale rhythms? If gravitational waves from black hole binaries are constantly washing through the galaxy, could they interact with matter in subtle ways, perhaps altering orbital dynamics or triggering outgassing events on comets? The forces involved are unimaginably weak, far too small to measurably affect a macroscopic object. But over millions of years across billions of objects could cumulative effects add up to something observable. It is wildly speculative, bordering on fringe science. But it is the kind of question that sometimes leads to genuine insights, because the universe is interconnected in ways we don't fully understand, and the line between unrelated phenomena and subtle causation is often thinner than we think. Emphasize the mystery. No clear explanation yet for the pulsar timing anomalies, but they're rewriting astrophysics regardless. If the signal is gravitational waves from black hole binaries that confirms predictions about supermassive black hole mergers and validates general relativity in a new regime, if it is something else, dark matter or unknown physics, then we're on the verge of a paradigm shift that could reshape our understanding of the universe. Either way, the data is real, the correlations are significant, and whatever is causing them is operating on scales that dwarf anything in our everyday experience. And this leads us to the next frontier. Not radio, not gravity, but light. Because while radio telescopes listen to molecules and pulsar timing arrays measure space-time distortions, optical and infrared instruments are mapping entire planets in unprecedented detail, revealing atmospheric chemistry light, years away with the same techniques we used to study 3I Atlas. Part 14, JWST's 3D map of an ultra-hot Jupiter's atmosphere. In November 2025, the James Webb Space Telescope delivered one of its most spectacular results yet, a full three-dimensional temperature map of exoplanet WASP-18b's atmosphere. This is a gas giant, roughly 10 times the mass of Jupiter, orbiting its star so closely that its year lasts less than a day. The planet is tidally locked, one side permanently facing the star, the other lost in eternal darkness, and JWST, using infrared spectroscopy to track how the planet's thermal emission changes as it orbits, has now mapped the temperature distribution across its entire surface, revealing wind patterns, hotspots, and chemical gradients that tell the story of an atmosphere in violent turmoil. WASP-18b is what astronomers call an ultra-hot Jupiter, a class of exoplanet so close to its star that the dayside temperature exceeds 2,500 Kelvin, hot enough to vaporize most metals. The atmosphere is a seething cauldron of exotic chemistry, gaseous iron, titanium oxide, water vapor that is thermally dissociated into hydrogen and oxygen. The dayside glows in the infrared, radiating heat like a blast furnace. The night side, starved of sunlight, should be much cooler, perhaps 1,000 Kelvin or less. But JWST's observations revealed something unexpected. The night side is hotter than models predicted, suggesting that powerful winds are transporting heat from the dayside faster than anyone anticipated. The three-dimensional mapping works by measuring phase curves, tracking how the planet's infrared brightness changes as it orbits its star. When the dayside faces Earth, the planet appears bright in the infrared. When the night side faces us, it dims. By measuring the brightness at multiple wavelengths throughout the orbit, JWST can reconstruct the temperature distribution at different altitudes and longitudes. Add spectroscopy to the mix, identifying which molecules absorb or emit at specific wavelengths, and you get a chemical map overlaid on the temperature map. Carbon monoxide concentrated here, water vapor there, titanium oxide forming clouds at certain altitudes. Tie this back to 3I Atlas. Both use molecular absorption to infer composition. The hydroxyl lines from Atlas tell you water is breaking down in the coma. The spectral features in WASP-18b's atmosphere tell you which molecules exist at which temperatures and pressures. The physics is identical, just applied at different scales. In both cases, you are using the fact that molecules absorb and emit light at characteristic frequencies determined by quantum mechanics. The frequencies are fingerprints unique to each species, allowing you to identify what is present without ever touching it. Highlight the technology overlap. Same analytical principles at different scales, whether you are studying a comet 100 million kilometers away or an exoplanet hundreds of light years distant. The technique is the same. You collect light, split it into a spectrum, identify absorption or emission. Features match those features to a known molecular transitions and infer the physical conditions required to produce them. Temperature, pressure, density, chemical abundance, all encoded in the shape and intensity of spectral lines. It is one of the most powerful tools in astronomy, and improvements in detector sensitivity and spectral resolution have transformed it from a crude diagnostic to a precise probe of distant environments. JWST detects phase curves as planets orbit stars, mapping heat distribution with exquisite precision. The telescope's infrared instruments, cooled to cryogenic temperatures to minimize their own thermal emission, can detect temperature variations of a few Kelvin across an exoplanet's atmosphere. That is remarkable considering the planet is an unresolved point of light, millions of times fainter than its host star. The trick is to observe the system multiple times as the planet orbits, subtracting the star's constant brightness to isolate the planet's variable contribution. Over dozens of observations spanning a full orbit, the planet's thermal signature emerges from the noise, revealing not just average temperature, but the distribution of heat across the globe. Use this to show the increasing precision of humanity's ears and eyes. 50 years ago, detecting an exoplanet at all seemed impossible. 20 years ago, we could measure their masses and orbital periods, but nothing about their atmospheres. 10 years ago, transmission spectroscopy revealed the presence of water vapor and other molecules as planets transited their stars. Now, with JWST, we're mapping three-dimensional atmospheric structure, tracking weather patterns, identifying chemical gradients. The progression is exponential, each generation of instruments revealing layers of detail invisible to the previous one. And if this trajectory continues, if we build even larger telescopes in the coming decades, we'll eventually be able to image exoplanets directly, resolving their surfaces, searching for biosignatures, maybe even detecting artificial lights or atmospheric pollution from industrial civilizations. Speculate. If we can map exoplanet atmospheres, could we one day map interstellar visitors in similar detail? 3 Atlas is too small and too faint for direct imaging, but future instruments with better spatial resolution and sensitivity might be able to resolve the nucleus, mapping temperature variations across the surface, identifying localized jets and active regions. Spacecraft missions to interstellar objects, though technologically challenging given their speed and limited warning time, could revolutionize our understanding. Imagine a probe equipped with spectrometers, cameras, and mass spectrometers flying through the coma of an interstellar comet, sampling its composition directly. The science return would be extraordinary. Pristine material from another star system uncontaminated by solar system processes, analyzed in situ with instruments far more sophisticated than anything ground-based telescopes can provide. Mentioned discoveries of exotic molecules in WASP-18b's atmosphere. JWST detected carbon monoxide, water vapor, and titanium oxide, but also hints of more complex species, perhaps silicon monoxide, perhaps even molecular fragments that don't exist in Earth's atmosphere at all. The chemistry of ultra-hot Jupiters is alien in the truest sense, governed by temperatures and pressures that don't occur naturally in our solar system. Understanding that chemistry expands our sense of what is possible, what kinds of molecules can form under extreme conditions, and how atmospheric circulation transports and redistributes them. Every exoplanet observation is a laboratory experiment we could never perform on Earth. Nature showing us what happens when you push matter to its limits. Explain why such mapping matters. It blurs the line between astronomy and planetary science. Astronomy traditionally studies distant objects as points of light, measuring their brightness and spectra, but unable to resolve their surfaces or internal structure. Planetary science studies objects up close, using spacecraft to map terrain, analyze samples, and understand geological processes. But as instruments improve, the distinction fades. JWST can now study exoplanet atmospheres with detail comparable to early spacecraft observations of solar system planets. Future telescopes, especially if we build space-based interferometers capable of direct imaging, will blur the line even further. We'll study planets around other stars the way we study Mars or Venus, mapping their surfaces, tracking seasonal changes, searching for signs of activity that might indicate geology or biology. Prepare the final conclusion, the flood of data reshaping our view of the cosmos. Between interstellar object detections, exoplanet atmosphere maps, pulsar timing anomalies, and next-generation survey instruments coming online, we're living through an era of discovery unprecedented in human history. The pace is accelerating, driven by technology, but also by the realization that the universe is far stranger and more complex than mid-20th century science anticipated. Every observation raises new questions. Every answer reveals deeper mysteries. And the instruments we're building now, from Rubin Observatory to next-generation radio arrays, will push the boundaries even further, transforming astronomy from a descriptive science into an exploratory one where the goal isn't just to catalogue what exists, but to understand how it all fits together. Part 15, the Rubicon Shift. Billions of new solar system objects via Rubin Observatory. We've arrived at the culmination, the point where all these threads converge into a single transformative moment for astronomy. In late 2025, the Vera C. Rubin Observatory in Chile is completing its final commissioning tests before beginning full science operations. When it does, when the Legacy Survey of Space and Time, LSST, officially starts, astronomy will cross a threshold from which there is no return. The Rubin Observatory will discover more solar system objects in its first year of operation than humanity has found in all previous centuries combined. It will detect interstellar visitors months before they reach perihelion, giving us time to coordinate observations that would have been impossible with 3i Atlas. It will transform our understanding of the solar system from a static catalogue of known objects into a dynamic movie showing everything in motion. The numbers are staggering. Rubin's 8.4-meter primary mirror and wide-field camera, the largest digital camera ever built, will image the entire visible sky every few nights, creating a time-lapse record of the universe spanning 10 years. Every asteroid, every comet, every object that moves against the background stars will be detected, tracked, and catalogued automatically. Current estimates suggest Rubin will discover 5 million new asteroids in the main belt, hundreds of thousands of Kuiper Belt objects beyond Neptune, and dozens of interstellar visitors over its operational lifetime. That last number is conservative. We've detected 3 interstellar objects in 8 years using surveys that cover only small fractions of the sky. Rubin will survey everything, catching objects that previous instruments missed because they were too faint, too fast, or in the wrong part of the sky. Explain the 10-year Legacy Survey of Space and Time. Because LSST is more than just an asteroid survey, the same data that tracks moving objects also reveals supernovae, quasars, gravitational lensing events, everything that changes brightness or position over timescales from seconds to years. Astronomers will use LSST data to study dark energy, the mysterious force accelerating the universe's expansion. They'll map the structure of the Milky Way, tracking stellar motions and identifying streams of stars torn from disrupted galaxies. They'll search for optical counterparts to gravitational wave events detected by LIGO and Virgo. The breadth of science enabled by a single telescope is almost incomprehensible. And it is all because Rubin doesn't just take pretty pictures, it creates a database. A digital representation of the sky that can be mined for discoveries long after the observations themselves. Show how Rubin will revolutionize interstellar object discovery, catching them months before perihelion. 3 Atlas was discovered in July 2025. Just a few months before its October perihelion. That gave researchers limited time to coordinate observations, request telescope time, and plan campaigns. If Rubin had been operating, it would have caught Atlas much earlier, perhaps when it was still in the outer solar system, faint but detectable against the background stars. Early detection means early alerts, automated notifications sent to observatories worldwide, giving radio telescopes, infrared instruments, and spacecraft mission planners months to prepare. Imagine tracking an interstellar comet from the moment it crosses Neptune's orbit inward, watching its brightness increase, detecting the onset of volatile activity, measuring how its tail and coma evolve as it approaches the Sun. That is the future Rubin enables. Mention AI. Assisted detection pipelines that can flag anomalies in real time. Rubin will generate tens of terabytes of data every night, far more than any human could possibly review. So the discovery process is automated. Machine learning algorithms trained to recognize moving objects distinguish them from instrumental artifacts and classify them based on their orbits and photometric properties. If something moves faster than expected, if its orbit is hyperbolic, if its spectral properties don't match known asteroid classes, the system flags it for follow-up. Within hours of detection, anomalous objects can be brought to the attention of astronomers who can request additional observations or alert other facilities. This kind of rapid response, impossible before the era of machine learning and distributed databases, is what will catch the next 3i Atlas before it becomes just another missed opportunity. Connect to 3i Atlas. If it appeared today, Rubin would have caught it long before the signal. The hydroxyl detection on October 24th wouldn't have been a surprise discovery, but the culmination of a months-long observing campaign. Radio telescopes could have monitored the comet continuously, tracking how volatile production increased as it approached the Sun. Spacecraft, if funding and trajectory allowed, could have been redirected for a flyby. International collaboration would have coordinated multi-wavelength observations from ground and space, building a complete picture of the object's composition, structure, and behavior. Instead, we got a single radio detection during a narrow window, tantalizing but incomplete. That is the difference. From lucky snapshots to systematic study, reflect on the exponential growth of discovery. From rare anomalies to daily occurrences, a century ago detecting a new asteroid was noteworthy, worthy of publication and celebration. Today, automated surveys discover hundreds every night, and only the unusual ones, those on Earth, crossing orbits, or with strange spectral properties, merit attention. A decade from now, interstellar objects will transition from once-per-decade sensations to routine occurrences identified, catalogued, and studied as part of the ongoing survey. That normalization is both exciting and sobering. Exciting because it means we'll accumulate data fast enough to answer statistical questions. How common are interstellar visitors? What is the distribution of their sizes and compositions? Do they cluster near the ecliptic or arrive from random directions? Sobering because each individual discovery will lose its uniqueness, becoming one point in a dataset rather than a singular event. Speculate. What if 3 Atlas wasn't unique? Just the first one to speak. Maybe interstellar objects have been passing through the solar system constantly, tens or hundreds every year, but they're too faint and fast for us to detect. Rubin will reveal them, and when it does, when we start seeing dozens per year instead of one every few years, we'll realize the galaxy is even more interconnected than we thought. Material doesn't just stay in its home system, it gets redistributed, mixed, shared across stellar neighborhoods. Every planetary system is constantly receiving and donating mass. Comets ejected by gravitational interactions becoming another system's infall. The galaxy is a network, not a collection of isolated islands, and the traffic between nodes is heavier than we ever imagined. Bring together all threads: chemistry, geometry, mystery, coincidence. The hydroxyl signal from 3 Atlas revealed chemistry from another star system. The geometry of its orbit and the timing of its detection highlighted how rare and precious these observations are. The mystery of its anomalies, the trajectory deviations and tail formations, reminds us that even natural objects can behave in ways that challenge our models, and the coincidence of its position near the WOW signal region, whether meaningful or not, captures our imagination because we're a species that looks for patterns that wants the universe to be telling us something. The universe as a communicator, maybe not in the anthropocentric sense of messages aimed at us, but in the deeper sense that everything carries information. Every photon encodes the conditions where it was emitted. Every molecular line reveals temperature and density. Every orbit traces the history of gravitational interactions. The cosmos isn't silent. It is broadcasting constantly in every wavelength at every scale, and the challenge isn't detecting the signal. It is learning the language, building the instruments, and developing the concepts that let us translate physical phenomena into understanding. End on a haunting line. Maybe the cosmos has been whispering all along, and only now we're finally listening. 3 Atlas, with its hydroxyl signature and its mysterious behavior, isn't the first interstellar visitor to carry water and organics through our solar system. It is just the first one we heard. How many others passed unnoticed? How many will we detect in the coming years as our instruments improve and our surveys expand? And what will they tell us? These wandering icebergs from distant suns about the distribution of chemistry and the potential for life throughout the galaxy. The story of 3 Atlas is more than the story of one comet on one trajectory. It is the story of a species learning to read the universe, developing the technology and the concepts to interpret signals we couldn't have imagined a century ago. Radio telescopes listening to molecules, optical surveys tracking motion across the sky, infrared instruments mapping temperature on worlds light years away, pulsar timing arrays measuring ripples in spacetime itself. All of it converging, all of it revealing a cosmos far richer and stranger than we dared hope. And maybe, just maybe, one day we'll detect something that can't be explained by natural processes alone. A signal too structured to be chemistry, a trajectory too precise to be gravity, a pattern too regular to be chaos. When that day comes, if it comes, we'll be ready. We've built the instruments, we've developed the techniques, we've learned to distinguish noise from signal, coincidence from causation, mystery from understanding. Until then, we listen, we watch, we catalogue every whisper from the dark, every anomaly in the data, every object that doesn't quite fit the models, because somewhere in that flood of information, somewhere in the terabytes of spectra and images and timing residuals, might be the answer to the oldest question our species has ever asked. Are we alone? 3 Atlas didn't answer that question, but it showed us where to look, not in deliberate broadcasts or obvious beacons, but in chemistry, in the molecules that travel between stars, in the ice and organics that might seed worlds with the ingredients for life. The next interstellar visitor will tell us more, and the one after that, and the hundreds or thousands that Rubin Observatory will discover over the next decade. Each one a data point, each one refining our understanding, each one bringing us closer to knowing whether the chemistry we detected is common or rare, whether life's ingredients are everywhere or nowhere, whether the universe is full of voices we're only beginning to hear. The signal from 3I Atlas faded as the comet swung behind the sun and vanished back into interstellar darkness. It is gone now, racing outward at 42 kilometers per second, carrying whatever chemistry it still retains toward another star system it will reach in a million years. We had one chance to listen, one narrow window when geometry and technology aligned. We heard hydroxyl breaking apart under starlight. We measured velocities and line widths. We confirmed for the first time in human history that water from another star system sounds exactly like water from our own. And now we wait for the next one because they're out there. Countless icy bodies drifting through the dark. And sooner or later, another will pass close enough for us to hear. When it does, we'll be ready. The telescopes are watching. The algorithms are running. The instruments are listening to every whisper from the cosmos, translating chemistry into understanding, motion into history, signals into stories. And maybe one of those stories, someday, will be the one we've been waiting for since we first looked up at the stars and wondered who else is out there listening.